There is a place in the cosmos where silence reigns more deeply than almost anywhere else, where gravity's pull fades into the void, where stars live and die unseen by cosmic neighbors, and where a single, defiant spiral of light spins alone in the dark. This is NGC 6503, a galaxy marooned at the edge of emptiness, known by a name that echoes its poetic solitude: the Lost Galaxy. But before we continue, subscribe to the channel so you don't miss out on any of these videos. This isn't just another faint smudge in a telescope. NGC 6503 exists on the edge of what can only be described as a cosmic desert, a void so vast, so hauntingly hollow, that the very concept of neighbor becomes irrelevant. Its nickname, the Lost Galaxy, isn't hyperbole. It's a reflection of its reality. It's a galaxy that seems to have escaped the crowd, slipped through the fingers of the gravitational web, and taken refuge at the frontier of known structure. The universe, vast as it is not evenly populated. Galaxies tend to cluster together in cities of stars, called groups, clusters, and superclusters, bound together by gravity and cosmic history. But not NGC 6503. Instead, it finds itself teetering on the edge of the local void, a region of the universe so devoid of matter that it's often described in hushed tones by cosmologists. Imagine living on the last lighted street of a city, staring into a boundless, dark countryside. That's where NGC 6503 stands, a lonely lighthouse at the border of cosmic civilization. When astronomers first turned their instruments to this enigmatic object, they may not have realized the profound metaphor it would become. In a universe where everything seems connected, where galaxies tug at each other, merge, collide, and co-evolve, NGC 6503 offers a different story, a tale of cosmic solitude. And yet, it is not a dying ember. It is not dim or inactive. Far from it. NGC 6503 glows brightly with new stars. Its spiral arms stretch confidently, its structure intact, its energy undiminished. It's not lost in the sense of forgotten. It's lost in the sense of singular, a voyager on the edge of something so immense that we still struggle to describe it. Why should we care about a galaxy that sits alone on the fringe of a void? Because in its silence, NGC 6503 speaks volumes. It teaches us about the forces that shape galaxies in isolation, about how the absence of interaction may affect cosmic evolution, and about the deeper architecture of the universe itself. It is a case study in loneliness and resilience. It challenges the assumption that all galaxies need companionship, need collisions, need chaos to grow and evolve. Here is a spiral galaxy, spinning gracefully in peace, surrounded by emptiness and yet radiating vibrant life. But perhaps, most hauntingly, NGC 6503 offers us a reflection. In our human experience, we too are often surrounded by vast silence, tiny in a boundless cosmos. And yet, like this lost galaxy, we shine, we spiral forward, and we try to understand our place in the grand design. So come closer. Peer into the darkness. Trace the elegant arms of this solitary beacon. Let us journey into the life and mysteries of the lost galaxy, a place where the universe whispers, and silence becomes a canvas for cosmic wonder. It was in the early glow of the modern astronomical age that NGC 6503 first came to human attention. The year was 1854, and the man behind the telescope was the German astronomer Arthur Auers, a name not as universally recognized as Galileo or Hubble, but one etched forever into the quiet lore of deep sky discoveries. Auers, meticulous and disciplined, wasn't looking for anything in particular. He was part of a generation still mapping the heavens star by star, nebula by nebula, logging and categorizing what the eye could glimpse and what the growing power of lenses could reveal. In that pre-spectroscopy era, the skies still held secrets tightly, offering only hints through the eyepiece. Telescopes of the mid-19th century had begun to unveil a more complex universe, one not just filled with stars but speckled with ghostly smudges, objects that refused to resolve into single points of light. NGC 6503 was one such smudge, perched near the North Celestial Pole, in the constellation Draco, the Dragon. Auers logged it carefully, as part of a larger effort to chart celestial positions with increasing accuracy. But at the time, he could not have known what he had found. It would take more than half a century before we began to understand that these hazy blobs were not nebulae within our own galaxy, but rather island universes, entire galaxies themselves. NGC 6503, quietly added to the New General Catalog, NGC, by John Lewis Emile Dreyer in 1888, became one of thousands of deep sky objects known more by catalog number than by myth or name. It's fascinating to consider how easily something as profound as this could go unnoticed by the public consciousness for so long. In an era where astronomers were captivated by the Messier objects and by the puzzling planetary nebulae, this dwarf spiral galaxy simply didn't scream for attention. There were no dramatic outbursts, no supernovae lighting it up for weeks on end, no close gravitational neighbors twisting its arms into spectacular shapes. It was, from the very beginning, easy to overlook. Lost not just in space, but in priority. And yet it waited. As technology advanced, so too did our ability to peer more deeply into the night. The invention of photographic plates in the late 19th century and spectroscopy in the early 20th century gave astronomers new tools with which to examine objects like NGC 6503. What once looked like a blurry ellipse could now be dissected, its light spread into a spectrum, its structure analyzed, its distance estimated. And it was through these advancements that astronomers began to see NGC 6503 not as a mundane entry in a star atlas, but as a galaxy in its own right, separate, structured, and spinning. By the mid-20th century, its identity was confirmed, a spiral galaxy roughly 17 million light-years away, lying close to the plane of the sky but in an unusually empty region of it. As deeper sky surveys catalogued the distribution of matter in the universe, NGC 6503's odd placement near the edge of the local void began to raise eyebrows. How had a galaxy formed there? Why was it alone? And how had it managed to survive without the gravitational interactions that so many other galaxies depend on for growth and transformation? The story of NGC 6503's discovery is less about a singular Eureka! Moment and more about gradual revelation, a creeping awareness, developing over decades, that this was no ordinary galaxy. It had slipped past the radar for 100 years, never entirely ignored but never fully appreciated either. And perhaps that's fitting. Perhaps that's the only way the lost galaxy could be found, not through drama, but through persistence. Through the patient accumulation of knowledge. A discovery that wasn't loud, but deep. Now, with modern telescopes orbiting Earth and spectroscopic surveys tracing the motion of galaxies across the sky, NGC 6503 has stepped into the limelight, not as the most massive, the most luminous, or the most active galaxy, but as one of the most enigmatic. It marks its place in human astronomical history not through shock and spectacle, but through quiet rebellion against the norm. It is a galaxy that defies classification by location, that challenges assumptions of clustering and interaction, and that reminds us that sometimes the greatest mysteries are those that slip through the gaps. Its journey from an anonymous entry on a chart to a key subject of cosmological study spans more than 150 years, and in that time, it has transformed from an overlooked haze into a symbol of cosmic solitude. It's not just the story of a galaxy, it's the story of our evolving perception, of how far we've come in our quest to understand the universe, and how much more still lies hidden in the shadows, waiting for someone to notice. To understand what NGC 6503 truly is, we have to peer past the poetic moniker and dive into its physical reality, a dwarf spiral galaxy, quietly rotating about 17 million light-years away from Earth. In cosmic terms, that's not terribly distant. It's a stone's throw across the vast ocean of space, just beyond the edges of our own local group. And yet, despite its relatively close proximity, NGC 6503 maintains a mystique that more flamboyant galaxies often do not. It is not just defined by its location or its solitude, but by the very nature of its structure and identity. The phrase dwarf spiral is important. Spiral galaxies are typically associated with grandeur, sprawling arms, massive bulges, and sometimes dozens or even hundreds of billions of stars. The Milky Way, for example, is a giant spiral stretching over 100,000 light-years across, packed with star-forming regions, a central bar, and a massive population of stars. But NGC 6503 is a smaller sibling in this spiral family. At roughly 30,000 light-years in diameter, it's only about a third the size of the Milky Way. And yet, despite this modest scale, it carries the signature elegance of a spiral system. Its structure features discernible spiral arms, clearly visible in high-resolution imagery from telescopes like the Hubble Space Telescope. These arms wind outward from a bright central region, which appears to house a small bar structure, a typical feature found in many spirals, though not as pronounced here as in larger systems. Dust lanes, star clusters, and glowing gas clouds trace the arms, signaling the presence of ongoing star formation, a hallmark of youthful, dynamic galaxies. This is not a dead or quiescent structure drifting quietly through the void. NGC 6503 is alive, busy shaping new generations of stars. Its mass, while significantly lower than that of large spirals, is still substantial in absolute terms. Astronomers estimate that NGC 6503 contains somewhere between 1 to 2 billion solar masses worth of stars, plus gas and dark matter, enough to form a thriving galactic ecosystem. And unlike many dwarf galaxies, which often fall into irregular categories due to their disrupted or chaotic forms, NGC 6503 maintains a coherent, organized spiral pattern. That makes it something of a rarity, a well-structured spiral galaxy, but on a smaller, more delicate scale. What makes NGC 6503 especially compelling is the environment in which it lives. It's one thing to find a spiral galaxy within the bustling filaments of the cosmic web, where interactions with other galaxies are common. But finding a structured spiral in near total isolation, on the edge of a void, is unusual. Spiral arms typically emerge and evolve in part due to gravitational influences, tidal forces, and interactions with neighbors. The very presence of spiral arms in NGC 6503 raises the question: how did this galaxy develop such well-defined features in isolation? Was it once part of a group that has since dissipated? Or is this spiral pattern a result of purely internal processes? In terms of its stellar population, NGC 6503 presents a blend of old and new. Its central region glows with the softer red and yellow hues of older stars, stars that may be several billion years old, while its outer spiral arms sparkle with brilliant blue regions, indicating the presence of hot, young stars formed relatively recently. These are massive, short-lived stars, often formed in clusters, illuminating their surroundings and providing a clear visual cue that the galaxy is still actively converting gas into stars. High-resolution ultraviolet and infrared imaging has revealed bright star-forming knots, and radio observations have detected cold hydrogen gas, the raw material from which stars are born. That's one of the fascinating contradictions of NGC 6503. It lives in an environment where almost nothing happens around it, and yet within itself, it is full of activity, like a campfire burning in the middle of a dark desert. It is both isolated and energetic, a testament to the resilience and complexity of galactic life. Its inclination, the angle at which we view it from Earth, is about 74 degrees, meaning it is tilted just enough for us to clearly observe both the spiral structure and some of the depth of the disk. It's not perfectly edge-on, which would obscure the arms in a thin line, nor is it fully face-on, which might flatten its appearance. Instead, it presents an ideal angle for analysis, allowing astronomers to explore both its surface features and its internal dynamics. Despite its small size and remote location, NGC 6503 has earned a place in many astronomical surveys, from early photographic catalogs to deep sky studies of galaxy formation. It shows us that even modest systems, when placed in the right cosmic context, can become keys to understanding larger truths. It's a reminder that classification, spiral, dwarf, isolated, is only the beginning of the story. The true nature of NGC 6503 lies in how it defies the expectations that those labels typically bring. There are countless dwarf galaxies in the universe. Many are irregular, many are satellites, many are being torn apart or consumed by larger neighbors. But NGC 6503 is different. It stands alone, not just physically, but conceptually. A solitary spiral, spinning peacefully on the edge of nothing, yet brimming with structure, life, and unanswered questions. It is a galaxy that whispers, not shouts. And yet, in its quiet rotation, it invites us to ask the most profound questions, not only about what galaxies are, but what they can be, and how the environment around them can shape their evolution in ways we are only beginning to understand. To understand the true essence of NGC 6503, you must know not just what it is, but where it is. And that's where things become especially intriguing. This galaxy doesn't sit comfortably nestled among dozens of neighbors. It doesn't lie in the crowded lanes of a galactic metropolis or a bustling supercluster. Instead, NGC 6503 holds its place at the edge of a vast and haunting emptiness, a region of space so devoid of matter that its very name evokes mystery and silence, the local void. Now, in the grand structure of the universe, galaxies are rarely isolated. Thanks to gravity, galaxies tend to gather in groups and clusters. These clusters stretch into long filaments, strands of cosmic matter woven together into what we call the cosmic web, the large-scale structure of the universe. Between these glowing filaments lie enormous voids, sprawling cosmic deserts where few, if any, galaxies reside. NGC 6503 occupies a unique position. It sits right on the edge of one of these voids, like a solitary outpost at the frontier of civilization. If you were to zoom out far enough from Earth, past the familiar outlines of the Milky Way and our satellite galaxies, and trace your view out toward the constellation Draco, you'd find NGC 6503 clinging to the boundary between known galactic territory and the uncharted dark. It's a location that is, quite literally, on the edge of nothing. The local void, the massive chasm beside it, is no ordinary empty space. It's estimated to span more than 100 million light-years across, a vast, yawning region of the cosmos containing hardly any matter at all. In contrast, our Milky Way is part of the local group, which is itself a small piece of the much larger Laniakea supercluster, an expansive collection of galaxies all gravitationally linked and flowing together through space. These structures are teeming with galaxies, massive ellipticals, swirling spirals, dwarf companions, and all the tangled gravitational drama that comes with close company. But NGC 6503? It decided to stay back, or maybe it was left behind. At its cosmic address, there's virtually no gravitational crowding, no cosmic tug-of-war between galaxies, no tidal interactions from nearby systems that so often reshape or warp spiral structures. Instead, it rests just barely on the populated side of the boundary, a liminal zone between light and darkness, activity and stillness, density and nothingness. Astronomers have taken great interest in mapping the peculiar velocities of galaxies, deviations from the universal expansion, and it's in these maps that the true position of NGC 6503 gains definition. Galaxies tend to move away from the local void, as though being pushed, or more accurately, as if the rest of the universe is being pulled toward areas of greater mass while the void simply fails to hold them. This behavior has allowed scientists to trace the contours of the void itself. And in doing so, NGC 6503 emerged as one of the few detectable galaxies marking its edge, like a boundary stone left behind by the formation of the universe. Imagine, for a moment, what the sky might look like if you stood inside NGC 6503 and looked outward. From Earth, our night sky is filled with stars and galaxies, an ocean of light stretching in every direction. But from the perspective of this galaxy, one side of the sky would be shockingly empty, a yawning darkness where virtually no galaxies lie. It would be like standing on a cliff and staring into a bottomless abyss, not of rock or air, but of pure absence. This is more than just a visual experience, it's a physical reality, one that shapes the fate and character of any galaxy residing in such a strange environment. This positioning, perched between the densely interconnected cosmic web and the vast loneliness of the void, makes NGC 6503 not only fascinating but scientifically invaluable. It offers a glimpse into what happens when a galaxy is cut off from the crowd, when it grows not in the bustling heart of a cluster, but in a quiet corner, far from the noise. It's a galactic hermit, spinning in silence, close enough to study but far enough to remain untangled by the web of gravitational society. And perhaps most profound is this: its location challenges how we think about cosmic structure itself. We tend to imagine the universe as balanced, evenly distributed, filled uniformly with galaxies from end to end. But NGC 6503's position reminds us that the universe has texture. There are ridges and valleys, cities and wastelands, and this galaxy happens to be sitting on the border between one of the most extreme contrasts of all. It is a sentinel, the last spiral before the silence begins. The universe, as vast as it isn't uniform. It's structured like a sponge or a cosmic web, with filaments of galaxies forming intricate strands that span across billions of light years, and between these strands lie the voids, the great underbellies of the cosmos. These voids are not just empty in a poetic sense. They are truly, staggeringly vacant, containing only a fraction of the matter found elsewhere in the universe. One of the most significant of these is the local void, a gaping, underpopulated expanse of space that yawns beside our own galactic neighborhood, and it is this void that defines the context, the environment, and much of the mystery surrounding NGC 6503. The local void is not a well-lit cosmic arena with elegant spirals and explosive starbursts. It is the Great Silence. Estimated to span over 100 million light-years across, it is one of the largest voids near our Milky Way. And it's not just a small patch of darkness, it's a region that stretches across a staggering portion of the nearby universe, containing far fewer galaxies than any typical region of comparable volume. To put this in perspective, a typical region of the universe that spans 100 million light-years might host tens of thousands of galaxies, of varying sizes and types. But the local void? It has only a handful, and even those are mostly on the periphery, like NGC 6503. First recognized in the late 20th century, the local void was identified through galactic redshift surveys and peculiar velocity studies, methods that allow astronomers to map the positions and motions of galaxies in 3 dimensions. These studies showed something odd, a distinct emptiness, a bubble in the universe where matter simply wasn't gathering in the way it did elsewhere. Our Milky Way, for example, is moving at roughly 600 kilometers per second relative to the cosmic microwave background radiation, and some of that motion appears to be a repulsion away from the local void, or rather, a gravitational pull from the denser regions beyond it. This suggests that the void's underdensity is real and powerful, exerting an influence not by pulling, but by simply lacking the mass to hold things in place. What makes the local void especially fascinating is that it's not an isolated bubble. It's connected to and defined by the surrounding cosmic web, which includes the local sheet, a relatively flat arrangement of galaxies in which the Milky Way resides. The local sheet borders the local void like a cliffside faces an ocean trench. On this metaphorical cliff is NGC 6503, hanging precariously close to the edge, one of the few galaxies marking the boundary between something and almost nothing. This is not merely an observational oddity. It has profound implications for cosmology, galaxy formation, and our understanding of how matter organizes itself in the universe. The local void gives astronomers a natural laboratory to test the predictions of the lambda cold dark matter model, which is the current standard model of cosmology. According to this model, matter clumps together over time due to gravity, forming filaments and walls, while dark energy accelerates the expansion of the universe, stretching and deepening the voids between them. The local void is a perfect test site for observing this process in action. Unlike the dense environments of galaxy clusters, which are noisy and turbulent with mergers, interactions, and rapid evolution, voids like the local void offer a pristine view of a galaxy's unperturbed life. In dense clusters, galaxies are often stripped of their gas, distorted by gravity, or even cannibalized by larger neighbors. But in the local void, there's room to grow, evolve, and survive without being knocked off course by others. The lack of gravitational disturbances gives rise to galaxies that may evolve more slowly, retain more of their original structure, and show us what galactic life might look like in cosmic isolation. But even within the void, it's not completely empty. There are occasional dwarf galaxies and threads of dark matter. These threads, while incredibly sparse, may stretch through the void like gossamer trails of gravity. Some theories even suggest that these invisible dark matter filaments are what allow galaxies like NGC 6503 to exist where they do, clinging to the edge of a faint gravitational structure that stretches across the emptiness. Interestingly, the void may be growing. As the universe expands, and especially under the influence of dark energy, voids are expected to expand faster than the dense regions. The reason is simple: gravity in denser regions slows the expansion locally, while voids, with less matter, expand faster. Over cosmic time, the local void may become even emptier, pushing the galaxies at its edge even farther apart. NGC 6503, already a galaxy on the edge of nowhere, may one day find itself even more isolated than it is now, a lone witness to the universe's slow unraveling. There is something haunting about the local void. Not because it's dark, darkness is everywhere in space, but because of its absence of structure, its resistance to the kind of cosmic architecture we've come to expect. It's a reminder that the universe is not a neatly arranged grid of stars and galaxies, but a wild and uneven expanse, shaped by the chaos of the Big Bang and the subtle dance of gravity over billions of years. It's a place where the laws of physics still apply, but where their consequences are profoundly different than in the crowded neighborhoods of space. For NGC 6503, being on the edge of the local void is not just a geographic fact, it's a defining feature of its identity. It has not had the typical galactic upbringing, surrounded by peers. It hasn't been stirred by frequent encounters or battered by gravitational tides. Instead, it has grown in solitude, shaped mostly by its own internal processes and whatever faint gravitational echoes ripple out from the cosmic web. This makes it invaluable to astronomers who seek to understand how much of a galaxy's evolution is driven internally, versus how much is dictated by its environment. The local void is a cosmic absence, but in its emptiness, it offers clarity. It peels away the complications of clustered environments, and lays bare the bones of galactic evolution. And for that reason, it is not a place of nothingness, but a place of profound scientific opportunity. NGC 6503, perched delicately at its border, serves as a signpost, marking the beginning of the unknown and inviting us to peer into it. As we look deeper into the universe, with ever more powerful telescopes and more refined maps of matter and motion, the local void remains a frontier, not just of space, but of understanding. And NGC 6503 is our guidepost, our companion at the edge of this vast, mysterious abyss. It's more than just a galaxy, it's a cosmic outlier, standing watch over the great silence that stretches beyond. Cosmic isolation is not merely about distance, it's about the absence of influence, the removal of gravitational chatter that defines most galaxies' lives. For NGC 6503, cosmic isolation means existing in a part of the universe where the gravitational grip of neighboring galaxies is practically non-existent, where its motion, structure, and evolution are shaped almost entirely by its own mass and internal processes. To be in such a state is to live without interruptions, without cosmic collisions, without nearby rivals to nudge, distort, or consume. In the crowded corridors of the universe, galaxies live active, interactive lives. They tell down one another, spiral into one another, and sometimes tear each other apart. These are not rare events. Galaxy mergers, tidal disruptions, and group dynamics are commonplace. The Milky Way, for example, is surrounded by dozens of satellite galaxies, is currently cannibalizing several of them, and is on a slow-motion collision course with Andromeda. These interactions play a pivotal role in shaping a galaxy's size, shape, star formation rate, and overall destiny. But NGC 6503? It's alone. To understand what that means, we must look at how gravity works on the scale of galaxies. Gravity is not just a force that holds planets in orbit around stars. It's the fundamental architect of structure in the cosmos. Clusters of galaxies are bound together by their mutual gravitational pull, forming massive halos of dark matter that influence everything from gas clouds to stellar evolution. In these dense regions, the gravitational potential is steep. Galaxies move quickly, stars form violently, and cosmic evolution proceeds like a boiling pot. NGC 6503, perched on the fringe of the local void, resides in the opposite of that environment. Here, the gravitational potential is shallow. There is no crowd of galaxies pushing and pulling on it. No major galaxy to interact with, no swarm of dwarfs falling in, no galaxy clusters exerting tidal forces across millions of light years. Instead, it sits in relative gravitational silence. This silence brings consequences. In denser environments, galaxy interactions trigger starbursts, intense episodes of star formation, as gas is compressed by gravitational encounters. But in isolation, these triggers are absent. Instead, any star formation must occur through slower, more self-regulated processes. This gives astronomers a chance to observe what a galaxy might look like if left largely undisturbed for billions of years. Cosmic isolation also affects the growth and mass acquisition of a galaxy. Galaxies grow by accreting gas and merging with others. The Milky Way's current shape is partly the result of a long history of mergers, some violent, others gentle. NGC 6503, with no major mergers in sight, likely retains more of its original form. It may be one of the few galaxies whose spiral structure has not been twisted by nearby interactions. Its mass growth would have depended mostly on the gradual accretion of intergalactic gas, not on the more dramatic consumption of companion galaxies. Gravitational isolation also limits the inflow of material. In clustered environments, the inflow of cold gas, fuel for star formation, is often enhanced by gravitational infall, or even stripped from other galaxies. But NGC 6503 must rely on the modest, slow intake from whatever sparse filamentary structure may connect it to the broader universe. This shapes its star formation history, possibly causing a slower, more sustained pace, rather than bursts triggered by collisions. There's also the matter of dark matter halos, the invisible scaffolding around galaxies that governs their formation and motion. In denser areas, the halos of galaxies can overlap, influence each other, and interact in complex ways. In isolation, a galaxy like NGC 6503 can maintain a more pristine dark matter halo, undisturbed and spherical, allowing scientists to model and study dark matter distributions without the added complexity of nearby gravitational chaos. This makes NGC 6503 a valuable subject for dark matter studies, providing a clearer picture of how halos behave in quiet zones of the universe. But isolation is not just physical, it's also temporal. Without nearby galaxies to speed up its evolution through mergers or gas stripping, NGC 6503 evolves on a different timescale. It's not being reshaped by external forces. Its spiral arms are likely more stable over longer periods. Its central structure, including the possible lack of a supermassive black hole, may reflect this isolation too, a cosmic childhood that was never interrupted. And yet, despite this solitude, NGC 6503 is not a relic. It is not a galaxy that has withered in the dark. On the contrary, it is vibrant, forming stars, glowing with energy, and spinning confidently. This underscores one of the most profound realizations about cosmic isolation. It doesn't mean stagnation. In fact, it may be the key to long-term stability and self-determined evolution. Free from the gravitational drama of neighbors, NGC 6503 has become a control group in the experiment of galactic evolution, a baseline against which we can compare the chaotic lives of galaxies and clusters. Its isolation also offers psychological resonance. In a universe filled with complex relationships and interdependencies, there is something profound in the idea of a galaxy going it alone, forming stars, maintaining structure, radiating light across millions of light years, without the need for a surrounding crowd. It reflects the truth that solitude, though rare, is not synonymous with decline. It can also mean independence, stability, and resilience. For astronomers, NGC 6503's cosmic isolation makes it more than just a scientific curiosity. It's a lens through which we can understand how galaxies behave when left to their own devices, a reminder that the environment shapes everything, from the way galaxies spin, to the way they age, to whether they live in light or darkness. In the end, NGC 6503's gravitational solitude is not an absence, it is a canvas. And from this stillness, a complex, living galaxy has emerged, proving that even at the edge of the void, beauty and motion continue. NGC 6503, though impressive in its solitude and structure, is a galaxy of modest proportions. It doesn't stretch across the cosmic landscape with the grandeur of a giant like the Milky Way or the elliptical behemoths found in dense clusters. Instead, it spans a more humble 30,000 light-years in diameter, making it significantly smaller than our own galaxy, which measures over 100,000 light-years across. To put that into perspective, the Milky Way could theoretically fit more than 3 NGC 6503 side by side within its span. Yet within this smaller frame, NGC 6503 packs a remarkable amount of complexity. Its spiral arms curl gracefully outward, its central region shines with tightly knit stars, and its gas and dust disks are active with ongoing star formation. It is, in every structural sense, a full spiral galaxy, just downsized, as if the universe chose to paint on a smaller canvas while maintaining all the intricate detail. In terms of stellar population, the difference is just as stark. The Milky Way hosts an estimated 200 to 400 billion stars, while NGC 6503 is believed to contain only a few billion at most. This dramatic disparity in star count emphasizes its classification as a dwarf spiral galaxy, a classification that speaks more to scale than to structure or function. Despite its smaller size, NGC 6503 isn't primitive or malformed. It's a finely shaped spiral, bearing the hallmarks of well-organized galactic architecture. Its thickness, although less precisely measured than its diameter, follows similar scaling. If the Milky Way's disk is several hundred to 1,000 light-years thick in its central bulge, NGC 6503's disk is likely much thinner and less dense, with a relatively smaller bulge at its center. However, despite being less massive, the galaxy's internal gravity is still sufficient to maintain orderly rotation, spiral arm definition, and containment of its interstellar medium. What's remarkable about its size is not just how small it is, but how much it does with so little. A galaxy of this scale could easily have ended up as a featureless dwarf, or a chaotic irregular blob, especially in such isolation. But NGC 6503 seems to have taken its compact form and evolved with an unusual degree of grace and precision. Its spiral arms are clearly visible, stretching out in organized curves. These arms are active, hosting clusters of young blue stars that shine like jewels embedded in the galactic disk. And although the galaxy lacks the gravitational complexity of larger systems, it has nonetheless avoided internal collapse, dispersal, or stagnation. Astronomers have long been fascinated by this efficient use of space. NGC 6503's rotation curve, how quickly stars and gas move at various distances from the center, shows evidence that it holds together tightly, likely thanks to a significant dark matter halo. In other words, its relatively low stellar mass doesn't tell the full story. Much of the galaxy's mass may be invisible, hidden in the form of dark matter that provides the necessary gravitational glue to bind such a small, yet ordered, galaxy together. Its small size also impacts its gravitational influence beyond its borders. While the Milky Way and other massive galaxies can dominate the motion of dozens or even hundreds of nearby galaxies, NGC 6503 is likely gravitationally self-contained. Its reach into the surrounding space is limited, another factor that contributes to its profound cosmic isolation. It doesn't control a system of satellites or companions. It doesn't appear to have torn apart smaller galaxies in its past. It exists more like an island than a continent, self-contained, with just enough internal coherence to maintain order but without the mass to exert significant power over its surroundings. The star formation occurring within NGC 6503 also reflects its scale. It lacks the explosive, chaotic starburst regions found in larger galaxies experiencing mergers or active feeding from the intergalactic medium. Instead, its star formation is steady and dispersed, occurring mainly in its spiral arms. This gentler pace may be linked to its smaller size and lower mass, which prevents the kind of gravitational compression that ignites starbursts in more massive or more disturbed galaxies. Even within this smaller galaxy, there is diversity of age and composition. Its central region is populated with older, redder stars that have settled into long orbits, while the outer arms glisten with the youthful blue light of recently formed stars. The distribution of gas and dust, while more limited in volume than that of the Milky Way, is sufficient to sustain ongoing stellar birth, further evidence that NGC 6503, while small, is far from inert. Another notable trait of smaller spiral galaxies is the lack of a supermassive black hole, a characteristic that has been tentatively observed in NGC 6503 as well. While this will be discussed in more depth later, its absence, assuming it holds up to scrutiny, might also be related to the galaxy's size. Supermassive black holes are often formed and grown through galactic mergers and inflows of mass, processes that NGC 6503, in its calm corner of the cosmos, seems to have largely avoided. In size, mass, and population, NGC 6503 is a miniature compared to galactic giants. But its elegance lies in its coherence. This is not a fragment or a malformed remnant, it is a complete, functioning spiral galaxy, compact yet ordered, isolated yet active. Its 30,000 light-year diameter represents a space filled with complexity, where the same fundamental laws that govern Andromeda or the Milky Way play out on a smaller, quieter scale. So while the numbers might place it in the dwarf category, NGC 6503 stands tall in the stories it tells astronomers. It shows us that galaxy evolution is not purely the realm of the massive. That structure, beauty, and function can emerge even in the limited bounds of a smaller system. It is a reminder that in the vast orchestra of the universe, even the smaller instruments have their part to play, and can play it beautifully. NGC 6503 sits in a unique category of galactic classification that both defines its structure and sets it apart from many of its peers. It's officially recognized as a dwarf spiral galaxy, a designation that tells us a lot more than just its size. It paints a picture of its internal architecture, star-forming behavior, and evolutionary history. This classification is like a quiet badge of cosmic identity, revealing what kind of galaxy it is, how it moves, how it lives, and how it likely came to be what it is today. To begin, we must understand what it means to be a spiral galaxy. Spiral galaxies are one of the most iconic and recognizable types in the universe. They are defined by their flat, rotating disks of stars, gas, and dust, often adorned with spiral arms that wrap around a more spheroidal central bulge. These arms are typically home to active star formation, as gas clouds are compressed by density waves and transformed into bright, hot stars that illuminate the arms with a characteristic blue glow. NGC 6503 possesses all of these traits, though in a scaled-down form. Despite its dwarf status, it maintains a coherent spiral structure with multiple arms. Observations, particularly from the Hubble Space Telescope, reveal that its arms are well developed and contain active star-forming regions. This places NGC 6503 firmly in the spiral category, proving that even smaller galaxies can maintain the complex internal dynamics required to form and sustain spiral arms. What's especially fascinating about NGC 6503 is that it appears to sit on the border of several classifications. In the Hubble tuning fork diagram, a system used by astronomers to categorize galaxies, it fits best within the SA/SCD category. This notation breaks down into several key pieces. SA means the galaxy is unbarred or only weakly barred. While there may be some evidence of a short central bar in NGC 6503, it's not as pronounced as in strongly barred spirals like SBB or SBC types. S indicates that the spiral structure originates directly from the central region, rather than being shaped by a strong bar. CD refers to the looseness of the spiral arms and the relative size of the central bulge. A C classification suggests open arms and a small bulge, while D implies even looser, more fragmented arms, so CD reflects a kind of transitional state. This places NGC 6503 in the realm of late-type spirals, meaning its spiral structure is still present and fairly prominent, but its bulge is relatively small compared to early-type spirals like SAW or SB galaxies, which feature larger, more dominant central regions. Its central bulge, while not as dominant as those found in massive spirals, still plays a key role. This central concentration of stars forms a bright, rounded core, a spheroidal structure filled with older stars. It lacks the enormous gravitational influence seen in larger galaxies' cores, partly due to its smaller mass and possibly the absence of a central supermassive black hole. Still, it acts as the gravitational anchor for the entire system, stabilizing the disk and spiral arms as the galaxy rotates. These arms, observable in both visible and ultraviolet light, are not uniform or symmetrical. They twist gently, containing patchy star-forming regions and lanes of interstellar dust. These irregularities are common in dwarf spirals, which, due to their lower mass and weaker gravitational fields, are more susceptible to internal instabilities and subtle fluctuations. But despite this, the overall spiral pattern remains visible and coherent, especially when viewed with high-resolution imaging. It's worth noting that spiral galaxies of this size are not especially common. Many dwarf galaxies in the universe tend to fall into the irregular category, lacking a defined structure due to turbulent star formation histories or past gravitational interactions. Others, like dwarf ellipticals, lose their gas and fade into more spherical shapes. That's what makes NGC 6503 stand out. It's a small galaxy with large-scale organization, a miniaturized version of a grand design spiral, operating far from the gravitational disturbances that so often deform galaxies of similar mass. Its disk is also relatively thin, consistent with spiral morphology. The presence of gas and dust, the defining star-forming ingredients, further cements its spiral classification. Emissions in H-alpha, ultraviolet, and infrared wavelengths show that these materials are not just present, they're actively fueling the birth of new stars, particularly in the spiral arms. The existence of this structured disk, with differentiated regions for star formation, is a testament to the galaxy's gravitational coherence and long-term stability. In the broader taxonomic tree of galaxies, NGC 6503 occupies a precious and informative branch. It shows that spiral structure can persist even without the massive environments and frequent interactions that usually define galaxy formation in crowded clusters. It suggests that the formation of spiral arms may not require the nudging of companion galaxies or the spiraling dance of mergers. Instead, it can emerge from internal density waves, differential rotation, and the quiet workings of gravity, even in solitude. Its classification as a dwarf spiral also opens doors for comparative studies. Astronomers use galaxies like NGC 6503 as control samples to understand how spiral galaxies evolve across mass ranges. By comparing its structure to that of giant spirals, scientists can test models of disk stability, angular momentum, and dark matter halo influence. It stands as proof that galaxy classification is not just about categorizing shapes. It's about unlocking the secrets behind those shapes, the processes that generate them, and the environments that allow them to persist. NGC 6503 is an outlier not because it's structurally bizarre, but because it's surprisingly orderly in a place where chaos, irregularity, or silence might have been expected. Its classification as a dwarf spiral is more than a label. It's a window into what galaxies can become when left to evolve without interference. A demonstration of how the universe assembles beauty at every scale, not just in its biggest creations. In a universe where galaxies often congregate like city lights seen from space, glowing clusters scattered along filaments of dark matter, NGC 6503 is striking for what surrounds it, almost nothing at all. Its neighborhood isn't just quiet, it's eerily vacant. While most galaxies are surrounded by siblings, companions, or rivals that influence their motion and structure through gravitational interactions, NGC 6503 resides in a cosmic cul-de-sac, with virtually no nearby galaxies to speak of. This solitude isn't an exaggeration or poetic embellishment, it is an empirical truth confirmed through detailed sky surveys. Observational data across multiple wavelengths, from optical to radio, consistently show a profound absence of other galactic bodies in its immediate vicinity. NGC 6503 has no major companions, no nearby dwarfs with clearly linked gravitational dynamics, and no evidence of past mergers or cannibalism that often scar the histories of galaxies in denser environments. In other words, it has grown, evolved, and spun in relative peace for billions of years, untethered by the kind of gravitational drama that shapes the lives of so many of its cosmic cousins. This near-total lack of neighbors makes NGC 6503 something of an oddity, especially considering its relatively organized spiral structure. Spiral arms often arise, or at least are enhanced, by gravitational nudges from nearby galaxies, whether through minor tidal interactions or full-blown mergers. And yet here is NGC 6503, a well-formed spiral without a community, an architectural marvel seemingly built in the middle of nowhere. The absence of nearby galaxies implies a lack of recent tidal interactions, which in turn supports what astronomers see in its morphology: relatively undisturbed spiral arms, a clean, unwarped disk, and a rotational symmetry that hints at long-term gravitational stability. There are no streamers of stars flung out by past collisions, no disturbed gas clouds suggestive of close encounters, and no satellite galaxies locked in orbit, slowly feeding material into the host. One might expect to find at least a few dwarf galaxies nearby, small, faint systems that often cluster around more massive hosts. The Milky Way, for instance, is surrounded by dozens of dwarf satellites. But in the case of NGC 6503, these potential companions are either absent or so faint and remote as to have no significant gravitational connection. This further underscores its position on the very edge of the local void, that vast underpopulated region of space which stretches out behind it like a cosmic abyss. The void doesn't just define the backdrop, it defines the context. In terms of cosmic geography, NGC 6503 lies at the interface between the local sheet, a flat, mildly populated structure where the Milky Way also resides, and the local void, which begins just beyond. On one side of this invisible boundary lies a bustling galactic suburb, on the other, an expanding realm of almost pure nothing. And NGC 6503 is essentially the last light on the road out of town, the final sentinel before the universe opens up into darkness. Astronomers studying the velocity field of galaxies in and around this region have noticed a peculiar motion. Many galaxies appear to be flowing away from the local void. This isn't because the void repels them, but rather because denser regions pull more strongly, and the void, being so empty, exerts little counterforce. NGC 6503, sitting on the edge, is barely anchored by the mild gravitational pull of the local sheet, while facing a gravitational vacuum on the other side. This dynamic accentuates its isolation. There's nothing behind it to pull it back, and no neighbor beside it to keep it company. The implications of this lonely positioning are more than just structural, they extend into how the galaxy lives. With no external gas inflows from galactic neighbors, NGC 6503 must rely solely on intergalactic gas accretion, or its own internal recycling to fuel star formation. This process is far slower than the dramatic gas exchanges seen in groups or clusters. Yet somehow, it has managed to sustain modest star formation for billions of years, like a desert flower that continues to bloom with only the faintest trace of moisture. Additionally, the lack of nearby galaxies makes NGC 6503 an ideal candidate for clean astrophysical modeling. When astronomers study galaxies, they're often forced to account for the influence of neighboring systems, which can complicate analysis of everything from dark matter distribution to stellar population histories. With NGC 6503, however, such complications are minimal. It exists in a vacuum of interactions, giving researchers a rare opportunity to observe what a spiral galaxy looks like when it evolves on its own terms. Its isolation may also explain some of its peculiarities, like the possible absence of a supermassive black hole at its center, a trait that sets it apart from most well-formed spirals. Without the galactic interactions that typically drive gas toward a galaxy's core, feeding and growing central black holes, NGC 6503 may have simply missed its opportunity to build one. Despite all this, it's important to understand that NGC 6503 is not alone in a literal sense. On large cosmological scales, no galaxy is completely alone. Galaxies are always connected to the dark matter web, the vast invisible scaffolding that holds the universe together. But in relative terms, compared to the busy galaxy clusters that populate the universe, it may as well be marooned. Its few closest observable neighbors are millions of light years away, far too distant to exert any significant gravitational influence. This isolation makes NGC 6503 an artifact of contrast, a structured, rotating body on the edge of oblivion. It glows quietly against the backdrop of one of the universe's greatest silences. It's the only voice in an empty room, the last page in a forgotten book, the one lighthouse on the edge of a lightless sea. And yet, that very solitude is what makes it valuable. For in its loneliness, we find clarity about how galaxies live, form, and shine when the universe leaves them completely alone. The nickname, the Lost Galaxy, isn't an official astronomical designation, but it has taken on a life of its own, an evocative, almost mythic title that captures both the scientific intrigue and the emotional resonance of NGC 6503. It is called Lost, not because we misplaced it, or because we stumbled across it too late, but because it exists in a realm so disconnected, so remote in the grand tapestry of cosmic structure, that it seems adrift, cut off from the hustle and gravity of galactic society. It is a galaxy that escaped the crowd, slipped through the filaments of the cosmic web, and settled at the edge of the known. In every sense, scientific, spatial, and symbolic, NGC 6503 is lost, and that makes it found. Let's first examine the scientific roots of the nickname. Astronomers began referring to NGC 6503 as the Lost Galaxy, in part because of its location on the outer fringe of the local void, a vast and underpopulated region of space that stretches over 100 million light-years across. Most galaxies are not found here. This is a realm where matter did not condense, where density fluctuations after the Big Bang left behind vast regions devoid of large-scale structure. Galaxies, clusters, and superclusters are the bright threads of the universe's cosmic web, but voids are the spaces in between, and NGC 6503 is right at the edge of one of the largest voids we know. This positioning makes it an outlier, a galaxy without a community, without the close gravitational relationships that define the life of most other galaxies. And because of this isolation, it essentially fell through the cracks of early mapping efforts. In the past, when galaxy surveys focused on denser regions of space, particularly those toward the Virgo cluster or deep into the local group, NGC 6503's lonely position meant it didn't draw attention. It's relatively close in cosmic terms, just 17 million light-years from Earth, but its location pointed not toward bustling galactic highways, but toward the silent expanse of the local void. It wasn't overlooked due to obscurity, but rather because it was on a path few telescopes were looking. In a universe where we tend to look where the light is, NGC 6503 was in the dark. There's also an aspect of the lost label that ties into the galaxy's unusual characteristics. It doesn't quite fit expectations. For one, its morphology, a clean spiral with active star formation, feels out of place in such a quiet and underpopulated part of the universe. Spiral galaxies are dynamic, evolving structures. They're shaped by interactions, fueled by external gas, and often defined by their gravitational relationships with neighbors. NGC 6503 doesn't seem to have had those interactions. It is, in that way, lost from the expected narrative. It defies the usual rulebook. A dwarf spiral like this one, in such extreme solitude, is scientifically rare. The nickname reflects this sense of it being a displaced character, a galaxy that should belong in a crowded space, but instead exists alone. Beyond the scientific and structural context, though, the moniker, Lost, also carries with it a powerful poetic weight, one that speaks to the human tendency to see stories in the stars. In the same way that we project emotion onto constellations or interpret nebulae as cosmic ghosts and stellar nurseries, we assign meaning to a galaxy's placement in the cosmos. NGC 6503, cast far from the others, becomes a metaphor for isolation, for wandering, for beauty and stillness. It is a galaxy without companions, a spiral without a chorus, a traveler on the edge of a void. The Lost Galaxy is not so much lost from our sight, but lost in the cosmic social sense, a galactic introvert orbiting far from the clamor of others. It's a name that evokes melancholy and wonder in equal measure. You can imagine it, turning in silence, its arms sweeping slowly through the darkness, with no nearby galaxies to interrupt its motion, no gravitational tides to distort its structure. It's a rare stillness. A peace. In this sense, the name, lost, might be better understood not as forgotten, but as free, unanchored, detached. NGC 6503 may not be lost in the tragic sense, but in the way that a lighthouse is lost to the sea around it, still shining, still steady, but forever solitary. And perhaps most fascinating of all is this: NGC 6503 may never have truly belonged to any group or cluster. It wasn't torn from a galaxy chain or flung out by gravitational recoil. It may have formed near the edge of the local void and simply stayed there, never drawing near to the dense filaments that govern so much of galactic life. If that's true, then it is not a lost member of a once crowded region, but rather a native of the emptiness, a galaxy that has always been adrift. This redefines what lost means. Not forgotten, not misplaced, but born in isolation, shaped by silence, and slowly spinning toward a future with no certain destination. For astronomers, this adds an element of existential intrigue. How many other galaxies might be like NGC 6503, existing at the margins, too faint, too distant, or too quiet to be noticed in current surveys? How many galaxies are still lost, not in the literal sense of location, but in the more elusive sense of understanding? NGC 6503 reminds us that even the known can remain mysterious, that even a visible galaxy can be hidden in meaning, if not in light. Ultimately, the nickname, the Lost Galaxy, speaks to the intersection of observation and imagination. It reflects what we know, that NGC 6503 is a gravitational outlier in a vast and quiet region of the cosmos, and what we feel, that this galaxy, spinning alone at the edge of a void, carries with it a story of solitude, survival, and silent persistence. It is a name earned not by being misplaced, but by being found in a place where nothing else exists. NGC 6503 may be classified as a dwarf spiral, but within its compact frame lies an intricate and fascinating internal structure, a miniature galaxy with an architecture worthy of any cosmic giant. Its morphology is a testimony to the subtle but powerful processes of galactic evolution that have shaped it into the elegant structure we see today. Despite its isolation and modest size, NGC 6503's form is full of complexity, displaying spiral arms, a bright core, and a possible bar-like central feature, all embedded within a thin, rotating disk. Let's begin with the most immediately recognizable component, the spiral arms. Observations from both ground-based telescopes and space-based instruments like the Hubble Space Telescope reveal that NGC 6503's arms are loosely wound, stretching gently outward from the core, forming what appears to be a flocculent spiral pattern. Unlike grand design spirals, which exhibit clearly defined, symmetric arms that wrap tightly around the galactic center, flocculent spirals like NGC 6503 are characterized by patchier, more fragmented arm structures. These arms don't trace perfect logarithmic spirals. Instead, they are intermittent and feathered, marked by bright blue knots of star formation interspersed with dark lanes of dust and cooler gas. These knots are clusters of young, massive stars, the result of recent or ongoing stellar nurseries. The fact that NGC 6503's spiral arms are still active in forming stars tells us that, despite its seclusion from the wider galactic community, the internal conditions within the galaxy, gas density, temperature, and pressure, are sufficient to trigger the gravitational collapse needed for stellar birth. Embedded within these arms are numerous H2 regions, clouds of ionized hydrogen gas that glow brightly under the ultraviolet radiation from nearby newborn stars. These glowing clouds trace the spiral arms like neon outlines, allowing astronomers to map the locations of recent star formation activity with high precision. These features also help define the arm structure more clearly in UV and H-alpha observations, even when the arms appear fragmented in optical wavelengths. Moving inward, we come to the central bulge and core region. NGC 6503 has a modest but noticeable bulge, far smaller than the massive central spheres of earlier type spirals like SAO or SB galaxies, but still a concentrated, spheroidal region of older stars. This central bulge contributes significantly to the galaxy's brightness and acts as the gravitational anchor from which the rest of the galaxy spins. However, it lacks the sheer density and gravitational dominance found in more massive galaxies. But this central region holds more than just an aging star population. There is strong evidence, especially from kinematic and photometric studies, for a bar-like structure at the heart of NGC 6503. Bars are elongated features made of stars and gas that stretch across the central region of a galaxy, often acting as channels for material to flow inward from the outer disk toward the core. In many galaxies, bars play a crucial role in funneling gas toward the central black hole or stimulating star formation in the core. In the case of NGC 6503, the bar is subtle, not a dramatic, extended structure like those seen in barred spirals such as NGC 1300 or our own Milky Way, but rather a short, weak bar that may not be visible in all wavelengths or to all observers. Infrared observations are especially helpful in identifying this feature, as they penetrate the interstellar dust and reveal the underlying distribution of stars. These studies suggest a bar aligned slightly off-axis from the spiral arms, hinting at mild asymmetries in the galaxy's internal dynamics. The presence of this bar-like feature suggests that secular evolution, slow, internal processes driven by the distribution and movement of stars and gas, may be at work in shaping the galaxy's internal structure. It also raises interesting questions about how such features form in isolation. In denser galactic environments, bars are often triggered or enhanced by tidal interactions, but in the quiet solitude of NGC 6503, the bar must have arisen through internal instabilities alone. That makes it a valuable laboratory for studying self-driven bar formation, free from external influences. Outside the central bulge and spiral arms lies the galactic disk, a flattened, rotating structure composed of stars, gas, and dust. In NGC 6503, the disk is relatively thin and extended, reflecting its low mass and tranquil evolutionary history. It lacks the warps and flares often found in galaxies that have undergone significant interactions. Its symmetry and smoothness suggest a galaxy that has been gravitationally undisturbed for billions of years. One of the most revealing insights into the structure of NGC 6503 comes from rotation curve analysis, studies of how the velocity of stars and gas changes with distance from the galactic center. These rotation curves are typically flat in spiral galaxies, implying the presence of dark matter extending well beyond the visible edge of the disk. NGC 6503 is no exception. Its rotation remains fast and consistent even at large radii, indicating that the mass distribution is dominated by an invisible halo of dark matter. This halo acts like a stabilizing force, helping the spiral arms and disk to maintain coherence despite the galaxy's low stellar mass. Also worth noting is the lack of a prominent stellar halo, the extended, spherical population of older stars that surrounds many galaxies. This may be a consequence of NGC 6503's isolation and lack of merger history. In galaxies like the Milky Way, the stellar halo is often composed of the remnants of smaller galaxies that were torn apart and absorbed. NGC 6503, having likely avoided such interactions, possesses a relatively clean and compact structure with little visible stellar material beyond its disk. Finally, its overall morphology is a marvel of balance. While small, NGC 6503 is not chaotic. While isolated, it is not simple. Its spiral arms swirl with purpose, its disk rotates with precision, and its central bulge quietly anchors a galaxy that seems to defy its environment. It has retained the hallmarks of spiral structure without the need for the constant reshaping pressures of a busy galactic neighborhood. It's as if NGC 6503, left to its own devices on the edge of a cosmic void, decided to build something beautiful, not grand or overwhelming, but precise, enduring, and quietly elegant. Its structure is a reflection of what galaxies can become when given space and time. It is the architecture of solitude, not chaotic, not stagnant, but ordered, evolving, and alive. One of the most fascinating and perhaps counterintuitive aspects of NGC 6503 is that, despite its profound cosmic solitude, adrift on the edge of the local void with no apparent neighbors to interact with or draw gas from, it remains actively forming stars. In a universe where galactic interactions, tidal forces, and mergers often ignite dramatic waves of stellar birth, NGC 6503 stands as a quiet yet powerful counterexample, a galaxy that has managed to maintain a self-sustaining star-forming ecosystem in isolation. The question becomes, how does a galaxy, so far removed from the bustling corridors of galactic clusters, continue to breathe life into stars? The answer lies in the internal reservoirs of gas within NGC 6503, especially cold molecular hydrogen and neutral atomic hydrogen, collectively known as the interstellar medium, ISEM. Star formation is fundamentally tied to the availability of this material. Without a sufficient supply of gas, galaxies become quiescent and fade into stellar senescence, their lights dimming as their stars grow old and die. But NGC 6503 has not reached this point. Its ISEM remains rich enough to fuel stellar birth, and its spiral arms are dotted with glowing H2 regions, those telltale signs of newly born, hot, massive stars ionizing the gas around them. The process begins with gravitational instabilities in the galaxy's rotating disk. As the galaxy spins, the density of gas and dust varies across its structure, especially within the spiral arms. These arms are not static, they're density waves, like standing waves in a river, where material temporarily accumulates before flowing onward. As gas clouds pass through these denser regions, the pressure and density increase. If conditions are right, the gas cools and collapses under its own gravity, fragmenting into dense molecular clouds, the cradles of star formation. Within these clouds, small pockets become unstable, triggering further collapse. As the pressure and temperature rise, nuclear fusion ignites, and new stars are born, often in clusters, often accompanied by bright emission nebulae. These young, massive stars shine intensely in the ultraviolet, ionizing the surrounding gas and creating glowing clouds of hydrogen that are visible across vast distances. In NGC 6503, these H2 regions can be clearly seen in both optical and infrared surveys, highlighting areas of recent and ongoing star formation. And it's not just happening in the arms. Star formation in NGC 6503 also occurs in more dispersed patterns across the disk. Infrared and ultraviolet data reveal that even the interarm regions show signs of activity. This suggests that, while the spiral arms help concentrate gas and trigger star formation, the conditions throughout the disk remain conducive to star birth. The galaxy, though smaller than the Milky Way, has a disk that is still rich in the elements necessary for stellar generation. But where does this gas come from, especially in such a remote and isolated environment? In many galaxies, external gas infall, drawn from surrounding galaxies, streams, or mergers, replenishes the ISEM. NGC 6503 lacks such companions, so astronomers believe its gas supply has either been conserved over billions of years or is being slowly replenished from the intergalactic medium, IGM. Even in voids, low-density filaments of gas exist, remnants of the primordial hydrogen that filled the early universe. Over long time scales, galaxies can accrete this material gradually, like a sponge soaking up humidity from the air. Though the inflow is slow, it's steady enough to sustain low to moderate rates of star formation. This leads to another surprising aspect of NGC 6503, its star formation rate, SFR, while not high, is remarkably consistent for a galaxy of its size and isolation. Estimates vary depending on the measurement technique and wavelength used, but the SFR is typically on the order of 0.1 to 0.3 solar masses per year. This may seem small when compared to the Milky Way's SFR of around 1 to 2 solar masses per year, but it's proportionally robust for a galaxy only 30,000 light-years across and much lower in mass. Importantly, this SFR appears to have been stable over extended periods, indicating that NGC 6503 is not undergoing a short-lived starburst, but rather experiencing a long-term, sustainable mode of star formation. This steadiness is further supported by its stellar population mix. The galaxy contains both old, red stars in its bulge and disk, and younger, blue stars in its spiral arms and outskirts. This diversity suggests that NGC 6503 has been forming stars for billions of years, never rapidly exhausting its gas, never going completely dormant. This measured pace of star formation may be precisely because of its isolation. In denser environments, galaxies are often disrupted, colliding, stripped of gas, or pushed into starburst episodes that burn through their fuel rapidly. NGC 6503, left alone, has had the luxury of evolving without these disturbances, allowing it to consume its resources gradually and maintain a balanced internal ecology. The calm of its surroundings also means that the gas dynamics within the galaxy are not being agitated by external forces. There are no large-scale tidal flows, no intergalactic shocks, no incoming gas-rich dwarfs dumping material into the system. What remains is a galaxy in dynamic equilibrium, where internal gravitational forces, differential rotation, and the slow recycling of stellar material through supernovae and stellar winds are sufficient to keep the ISM replenished and active. Interestingly, despite its moderate star formation, NGC 6503 does not appear to have significant large-scale outflows, or winds. In starburst galaxies, intense periods of stellar birth often create galactic winds that blow material out of the disk, heating the circumgalactic medium and removing star-forming gas. But in NGC 6503, the lack of such explosive events has allowed it to hold onto its gas, further contributing to its long-lived star-forming capability. Additionally, studies of the galaxy's metallicity, the abundance of elements heavier than helium, reveal that NGC 6503 has a metallicity gradient, with richer, more metal-heavy regions near the core and lower metallicity zones toward the outskirts. This pattern is consistent with slow, inside-out growth, where the central regions have undergone more generations of star formation and stellar recycling. It also underscores the idea that the galaxy has evolved gradually and internally, without major mergers to stir and homogenize the contents. All of this makes NGC 6503 a textbook case for sustainable galactic evolution. It's not flashy. It doesn't undergo the dramatic fireworks of starburst galaxies or the violent cannibalism of major mergers. Instead, it offers a different kind of story, one of stability, patience, and quiet creation. It's a galaxy that forms stars not because it's been shocked or disturbed, but because it has all the tools it needs and the peace to use them. In essence, NGC 6503 shows us that star formation doesn't require chaos. It can happen in quiet corners of the cosmos, far from the noise and traffic of the galactic superhighways. It can unfold slowly, gracefully, over billions of years. This galaxy, spinning at the edge of a void, proves that isolation does not mean dormancy. It means freedom. And in that freedom, it has chosen to keep creating light. In the heart of nearly every large galaxy, including our own Milky Way, lies a cosmic beast, a supermassive black hole, an object so dense, so gravitationally intense, that not even light can escape its grasp. These black holes often weigh millions or even billions of times the mass of our Sun and exert tremendous influence over their host galaxies, from the motion of nearby stars to the regulation of star formation itself. They are thought to be fundamental components of galactic evolution. And yet, in the case of NGC 6503, the story appears to be different. Here, we find a curious absence, a void within a galaxy already on the edge of one. For years, astronomers have turned their instruments toward NGC 6503's bright core, seeking signs of a central black hole, particularly one massive enough to fit the supermassive category. These searches rely on several techniques, including high-resolution spectroscopy to detect the rapid orbital motion of stars near the core, X-ray observations to look for accretion signatures, and radio mapping to uncover hidden jets or emissions associated with active galactic nuclei, AGN. But all these efforts have come up short. There is no compelling evidence that NGC 6503 contains a central black hole of any significant size. If one exists, it must be extraordinarily small by galactic standards, perhaps only a few tens of thousands of solar masses, rather than the millions or billions observed in galaxies like the Milky Way or Andromeda. Alternatively, it may be entirely absent, making NGC 6503 one of the rare known examples of a spiral galaxy without a central black hole. This is not just a trivial omission, it challenges a major paradigm in astrophysics. The prevailing theory is that galaxies and their central black holes co-evolve, each feeding and growing in tandem. In the early universe, as galaxies accreted gas and merged with others, black holes formed and grew in the centers, sometimes becoming active quasars, blazing with energy as they devoured matter. Over time, these central engines calmed down, but their mass remained, locked within a sphere of invisible influence. The tight correlation between a galaxy's central bulge mass and its black hole mass, the so-called sigma relation, supports this coevolutionary model. So, when a well-structured spiral galaxy like NGC 6503 breaks that correlation, it raises several provocative questions. Was this galaxy always missing a central black hole? Or did it once harbor one that somehow failed to grow? Could it have ejected its black hole during a gravitational interaction long ago, or perhaps never had the conditions to form one in the first place? One theory suggests that NGC 6503's isolation may have stunted the formation or growth of a central black hole. In denser galactic environments, frequent interactions funnel gas toward galactic centers, feeding both star formation and black hole accretion. But in the serene solitude of NGC 6503, where no major mergers have occurred and no tidal interactions have agitated the disk, there may have been no mechanism to drive gas inward with sufficient momentum to trigger black hole growth. In effect, the galaxy's peaceful existence may have denied it the violent ingredients typically required to forge a supermassive core. Another possibility is that the galaxy's central region does harbor a black hole, but it is too small and inactive to be detected with current instruments. Black holes that are not actively accreting matter, so-called quiescent black holes, are extremely difficult to observe, especially in galaxies without a tightly packed core of stars to provide detectable gravitational shifts. In this case, future telescopes, such as the upcoming Extremely Large Telescope, ELT, or space-based observatories with next-generation resolution, might yet uncover a faint dynamical signature. However, even if a small black hole were found, the absence of AGN activity in NGC 6503 is noteworthy. Galaxies with growing central black holes often emit strongly in X-rays or radio waves, thanks to the high-energy processes near the event horizon. NGC 6503 shows no such emissions. Its nucleus is silent, cold, and seemingly unburdened by any gravitational giant. And yet, intriguingly, the galaxy still maintains a central bulge, a feature typically associated with the presence of a supermassive black hole. This complicates the picture further. It means that a bulge can form and persist even in the absence of a central black hole, possibly through internal processes like secular evolution or slow gas inflow, rather than violent mergers or black hole feedback. This decouples two features that are often assumed to be inseparable and suggests that galactic evolution can proceed along alternative paths. The implications ripple outward. If more galaxies like NGC 6503 are discovered, structured spirals lacking central black holes, it could force a reconsideration of how universal the black hole galaxy connection truly is. Perhaps supermassive black holes are common, but not inevitable. Perhaps there is a spectrum of galactic formation histories, with some galaxies never needing or acquiring a central gravitational anchor. In fact, NGC 6503 may be the purest example of secular galactic evolution we know. It hasn't been shaped by merger-triggered starbursts or black hole feedback loops. Instead, it has evolved through slow, internal processes, density waves shaping the arms, bar-like instabilities nudging gas inward, and gentle star formation pulsing in and out across the disk. All of this has occurred without a central monster, without the dramatic influence of a black hole reshaping its surroundings. This absence becomes even more striking when we remember how common supermassive black holes are. They are found not only in massive galaxies but even in many dwarf systems. That NGC 6503, a relatively nearby, well-formed, star-forming spiral, may lack one entirely makes it a cosmic anomaly, and a crucial data point in the ongoing quest to understand the diversity of galactic evolution. In a galaxy defined by what it lacks, neighbors, interference, gravitational drama, it is fitting that its very center may also be defined by absence. Where we might expect to find the signature of darkness, we find only light, stars orbiting quietly, gas flowing without disruption, and a gravitational well that is deep but not bottomless. NGC 6503, The Lost Galaxy, continues to teach us that not every story needs a villain. Sometimes, the most telling truths come from what's not there. And in this case, the absence of a black hole may be just as revealing as its presence. Like a celestial painting rendered in a palette of time, NGC 6503 reveals its story not just through structure and silence, but through color. In astronomy, color is not just a matter of beauty, it's a window into the age, temperature, and evolutionary stage of stars, a cosmic fingerprint that tells us how a galaxy is living, changing, and remembering. In NGC 6503, the contrast between bright blue star-forming regions and older, redder stellar populations offers profound insight into how this isolated galaxy has evolved over billions of years. At first glance, especially through the eyes of the Hubble Space Telescope or ultraviolet-sensitive instruments, NGC 6503 glows with pockets of brilliant blue. These blue hues are not uniform. They are clustered, patchy, and strongly aligned with the spiral arms of the galaxy. This is no coincidence. These regions mark the galaxy's stellar nurseries, the locations where gas clouds have collapsed and ignited new generations of stars. The stars responsible for these blue glows are young, massive, and extremely hot. Stars like O-types and B-types, which are far more luminous than our Sun, radiate mostly in the ultraviolet and blue portions of the electromagnetic spectrum. But they live fast and die young, burning through their nuclear fuel in mere millions of years before ending their lives in spectacular supernova explosions. Their brightness, however, dominates the light from their surroundings, overpowering the softer glow of older stars and making star-forming regions stand out vividly in multi-wavelength observations. These blue regions of NGC 6503 are often accompanied by H2 emission nebulae, clouds of ionized hydrogen gas that shine with a characteristic pinkish-red color in visible light, but also emit strongly in ultraviolet. The presence of these emission nebulae is a direct indicator of recent star formation and serves as a highlighter tracing out the spiral arms, even when they appear fragmented or flocculent in structure. But between and beyond these luminous blue islands lie vast stretches of the galaxy glowing with cooler, redder light. These redder regions represent older stars, many of which formed billions of years ago during earlier phases of galactic evolution. Unlike their younger, bluer counterparts, these older stars are smaller, cooler, and much longer lived, K-type and M-type stars that can shine for tens of billions of years, long after the blue giants have gone supernova and disappeared. This distribution of color in NGC 6503 isn't random. It reflects the timeline of star formation across the galaxy. The central bulge, for instance, is dominated by these older, redder stars. It lacks the vibrant blue patches of the outer arms, suggesting that star formation in the core slowed long ago. What remains is a population of ancient stars, burning steadily, dimmer now, but deeply imprinted with the memory of the galaxy's earlier epochs. Between the bulge and the outer spiral arms lies a transition zone, a region populated by intermediate-age stars that exhibit yellow and orange hues, a blending of past and present. This gradient in stellar population reflects the inside-out growth pattern that many galaxies experience, where star formation begins in the center and slowly migrates outward over time. In NGC 6503, this pattern is especially well preserved, unblurred by the disruptive events of major mergers or galactic collisions. Additionally, the colors observed across NGC 6503 reveal something important about its chemical evolution. Young blue stars form from clouds of gas enriched by previous generations of stars, supernovae, and dying red giants that released heavier elements into the interstellar medium. By analyzing the metallicity, the abundance of elements heavier than helium, in different regions of the galaxy, astronomers can trace how star formation has recycled and redistributed material over time. NGC 6503 displays a metallicity gradient, with higher metallicity near the core and decreasing metallicity toward the outer disk. This gradient correlates with the color gradient. Older, redder stars in the center have enriched the environment more thoroughly, while the outer blue regions are forming from less processed, more pristine material. This is typical for spiral galaxies, but in NGC 6503's case, the gradient has remained undisturbed, frozen in place by the galaxy's long isolation. Another subtle but fascinating aspect of NGC 6503's stellar color map lies in the asymmetry of star-forming regions. While the galaxy maintains overall symmetry and structure, some sectors of its spiral arms shine more brightly in blue than others. This may suggest localized triggers of star formation, possibly due to internal density waves or residual feedback from previous stellar generations. It may also reflect minor asymmetries in the distribution of cold gas, perhaps sculpted by the gentle bar structure at its center. Importantly, the combination of these blue and red regions shows that NGC 6503 is a galaxy in balance. It's either bursting with unchecked star formation nor fading into quiescence. It has active, youthful zones coexisting with quiet, ancient populations, each telling part of the galaxy's evolutionary tale. This duality is rare and valuable, especially in such an undisturbed system. In denser environments, frequent interactions blur this clarity, mixing stellar populations, flattening gradients, and scattering star-forming regions through tidal forces. But NGC 6503 has remained pristine enough to preserve its history in color-coded detail. Observing this blend of hues through multiple wavelengths, ultraviolet for the youngest stars, optical for the general population, infrared for cooler, redder stars, offers a multidimensional view of the galaxy. It allows astronomers to piece together the chronology of star formation, migration of gas, and even the dynamics of disk evolution. Each color is a timestamp, and each glow is a diary entry in the long life of the galaxy. In short, NGC 6503's colors are a living spectrum of time. The blue regions whisper of now, pulsing with light from stars that will soon vanish. The redder zones echo of then, filled with stars that have watched the galaxy spin for billions of years. And together they form a chorus that spans cosmic epochs, a galaxy that may be lost in space, but not lost in memory. NGC 6503 may be a small and solitary galaxy, but when it spins, it whispers secrets about one of the universe's greatest enigmas, dark matter. While the galaxy's elegant structure and colorful star formation offer a visible story, its motion tells a hidden one, a gravitational tale written not in light, but in the quiet pull of mass we cannot see. To uncover this story, astronomers study the galaxy's rotation curve, a graph that plots the speed at which stars and gas orbit the center of the galaxy at various distances. And in the case of NGC 6503, that curve reveals something extraordinary. At first glance, one might expect NGC 6503's rotation to mimic that of our solar system. Objects closer to the center move faster, while those farther out slow down, following Keplerian decline. This makes sense if most of the galaxy's mass is concentrated in the central bulge. If there's little matter in the outer regions, gravity should weaken, and orbital speeds should drop accordingly. But when astronomers measure the actual velocities of stars and gas across the galaxy's disk, they see something entirely different. Using tools like radio telescopes to map neutral hydrogen gas, HI, and optical spectroscopy to track emission lines from glowing gas clouds, astronomers have constructed a precise rotation profile of NGC 6503. What they find is a rotation curve that rises quickly near the center, then flattens out, and remains remarkably stable well into the galaxy's outer regions. Even far from the luminous matter, well beyond where most stars reside, the orbital velocities do not decline. Instead, they maintain a steady speed of around 110 to 120 kilometers per second. This flatness is the hallmark of dark matter. It tells us that NGC 6503 contains much more mass than what we can see. If only the visible stars and gas contributed to the galaxy's gravity, then the outer regions should slow down. The fact that they don't implies the presence of a massive, invisible halo surrounding the galaxy, dark matter extending well beyond the luminous disk and contributing the gravitational pull necessary to sustain high orbital speeds at large radii. In fact, when astronomers model NGC 6503's mass distribution using its rotation curve, they find that visible matter alone can account for only a fraction of the galaxy's gravitational behavior. The stars and gas explain the inner rise in the curve, but not the extended flat portion. To match the observed velocities, a dark matter halo must be included, one that dominates the mass budget of the galaxy, especially in the outer regions. Estimates vary depending on the dark matter profile used, but models such as the Navarro-Frank-White (NFW) profile or pseudoisothermal halos suggest that NGC 6503's total mass, including dark matter, could be several billion solar masses, with dark matter accounting for the overwhelming majority. The visible matter, stars, gas, dust, may only comprise 10 to 20% of the total mass, leaving the rest as unseen gravitational scaffolding. What's remarkable is that this finding mirrors those seen in much larger galaxies, including the Milky Way. Despite its smaller size and isolation, NGC 6503 adheres to the same dark matter principles, reinforcing the idea that dark matter is a universal feature of galaxy formation, not just a quirk of massive or cluster-bound galaxies. Even out here, on the edge of the local void, the unseen mass holds sway. The galaxy's dark matter halo isn't just a static background. It plays an active role in shaping the galaxy's evolution. It stabilizes the disk, governs the speed of rotation, and protects the spiral structure from dissolution. In denser regions of space, interactions and mergers often disturb or strip dark matter halos, altering the internal dynamics of galaxies. But NGC 6503's solitude means its dark halo has remained intact and undisturbed, allowing for clean, uninterrupted observations of how such halos affect galactic motion. Furthermore, the galaxy's rotation curve allows astronomers to probe the distribution of dark matter within the halo. In particular, it provides insight into one of cosmology's key questions: does dark matter concentrate toward the center, a cusp, or does it flatten into a core? Some observations suggest that low-mass galaxies like NGC 6503 have core-like dark matter distributions, which may challenge predictions from cold dark matter simulations. While the data on NGC 6503 is not yet conclusive, it adds a valuable data point to the ongoing debate over the true nature of dark matter and its behavior on small scales. Interestingly, NGC 6503's rotation curve also hints at non-uniformities and subtle deviations, wiggles or bumps that may correspond to variations in the disk's mass density, spiral arms, or the influence of its small bar structure. These features are minor, but they demonstrate that the rotation curve is not merely a smooth function. It contains imprints of the galaxy's internal structure, and possibly even relics of past star-forming events or density wave activity. Moreover, the stability of the rotation curve over cosmic time raises questions about how galaxies like NGC 6503 maintain such orderly rotation in isolation. Without external perturbations, the internal angular momentum remains well preserved, suggesting a slow and gentle evolution. This again reinforces the value of NGC 6503 as a natural laboratory, a place where we can study the mechanics of rotation and dark matter without the noise of external interference. Another key takeaway from studying the rotation and movement of NGC 6503 is how it bridges the gap between dwarf galaxies and large spirals. Most dwarf galaxies are irregular in shape and often show declining or rising rotation curves without the classic flat portion seen in spirals. Large galaxies, on the other hand, have well-behaved rotation curves that extend into vast dark matter halos. NGC 6503, with its small size but large, flattened rotation curve, represents a middle ground, a dwarf spiral with big galaxy dynamics. This makes it especially important for testing modified gravity theories, like modified Newtonian dynamics, which attempt to explain flat rotation curves without invoking dark matter. Galaxies like NGC 6503, well-studied, isolated, and intermediate in mass, are crucial test cases for such theories. So far, however, the presence of dark matter still provides the most consistent and widely accepted explanation for its motion. In every sweep of its spiral arms, in every orbit of its stars and clouds, NGC 6503 affirms the gravitational pull of something unseen, something vast. It reminds us that galaxies do not move simply because of what we can measure in light, but because of what they are embedded in, the invisible web of mass that underpins the structure of the cosmos. For all its isolation, for all its soft blue glow and quiet spin, this little galaxy holds a powerful truth. The universe is shaped as much by darkness as it is by light. NGC 6503, drifting quietly on the edge of the local void, may seem like a small, tranquil place in the cosmos. But within its rotating stars and spinning gas lies a clue to something far greater, a gravitational ghost that shapes the structure and fate of the universe itself. This ghost is dark matter, the invisible substance that neither emits nor absorbs light but exerts a tremendous gravitational force. And despite its modest size, NGC 6503 is one of the most compelling laboratories for studying its elusive presence. Through careful analysis of velocity measurements, the galaxy has become a powerful witness to the existence and behavior of dark matter. The primary evidence comes from velocity studies, measurements of how fast stars and gas move within the galaxy. Astronomers use various techniques to construct detailed velocity maps, especially by observing spectral lines such as the H-alpha emission from ionized gas or the 21 cm radial line emitted by neutral hydrogen, Hi. These lines shift due to the Doppler effect, revealing how fast objects are moving toward or away from us at different points in the galaxy. By mapping these velocities across NGC 6503's disk, astronomers can build a complete rotation curve, a profile showing orbital speed as a function of distance from the center. And here lies the crucial clue. If NGC 6503 were composed only of the visible matter we can detect, stars, gas, and dust, then we would expect the rotation speeds to behave in a predictable way. Near the center, where most of the mass resides, velocities would rise sharply. Then, as we move outward and the density of visible material drops, the gravitational pull would weaken, and the orbital speeds should decrease. This is how planets behave in the solar system, where the sun holds most of the mass. But that's not what we see. Instead, NGC 6503's rotation curve rises near the core and then stays flat, extending far beyond the visible edge of the galaxy. The stars and gas continue to orbit at roughly the same speed, even where there is very little detectable mass. The only explanation that fits these observations is the presence of a massive, extended dark matter halo, a sphere of invisible material that surrounds the entire galaxy, providing the necessary gravitational pull to keep the outer parts spinning so rapidly. This pattern has been seen in many galaxies, but NGC 6503 is especially significant for a few reasons. First, it is relatively small and isolated. It is not part of a dense cluster where dark matter could be tangled or complicated by interactions. Its motion is largely unperturbed, meaning the rotation curve is clean, well-behaved, and easy to interpret. That makes the dark matter signature even more compelling, because there are fewer confounding factors that could mimic the effect. Secondly, the measurements for NGC 6503 are extraordinarily precise. Observations using the Very Large Array, VLA, and optical telescopes have traced gas and stellar motion out to large radii, giving a full picture of how the rotation behaves at both small and large scales. The transition from the luminous inner disk to the dark matter-dominated outer regions is smooth and consistent, exactly as models of dark matter halos predict. Even more fascinating are the attempts to model the dark matter distribution within the galaxy. Researchers have applied several halo profiles to match NGC 6503's rotation curve, including the Navarro-Frank-White (NFW) profile, which is derived from cold dark matter simulations, and the pseudo-isothermal sphere, which proposes a central core of roughly constant density. Interestingly, NGC 6503's data can be better fitted by the core-like profiles than by the steep central cusps predicted by the NFW model. This contributes to an ongoing debate in astrophysics known as the core crust problem, where real galaxies appear to have flatter inner density profiles than what standard cold dark matter models predict. NGC 6503 becomes a vital test case in this debate. Because it is not being torn or stretched by nearby galaxies, its dark matter halo likely represents a pristine, unaltered shape, ideal for comparing theoretical models to reality. These findings have ripple effects for cosmological theories. If low-mass galaxies like NGC 6503 consistently favor core-like dark matter halos, then either our understanding of how dark matter behaves must be revised, or additional processes, such as feedback from supernovae and stellar winds, must be invoked to explain how the central density could have been flattened over time. But the implications don't stop there. The very presence of such a massive dark matter halo around a small galaxy like NGC 6503 also lends strong support to the idea that dark matter drives galaxy formation. According to the lambda cold dark matter model, galaxies form within dark matter halos that emerged early in the universe. The gravity of these halos pulls in gas, which cools, condenses, and eventually forms stars. Without dark matter, galaxies would not have had the gravitational glue needed to pull themselves together. NGC 6503's well-structured form, preserved in isolation, reinforces this view. In addition to its flat rotation curve, NGC 6503 also shows other velocity-related signs of dark matter. The velocity dispersion, a measure of how randomly stars move in the vertical direction relative to the disk, is consistent with being supported by a deep, extended gravitational potential. The galaxy's disk would not be stable at such high rotation speeds unless there were an invisible mass reservoir adding extra gravity to hold it together. Otherwise, the disk would fly apart under its own motion. This gravitational anchoring affects more than just movement. It influences the stability of spiral arms, the ability of the disk to form stars, and even how the gas is distributed across the galaxy. In fact, simulations have shown that dark matter halos not only stabilize the disk but also affect how density waves propagate, possibly playing a role in organizing the flocculent spiral structure we see in NGC 6503 today. All of this makes the galaxy a cosmic Rosetta Stone for understanding dark matter in spiral systems. Its relatively clean environment, well-measured rotation curve, and intermediate size make it a near-perfect object to probe the properties of this mysterious substance. While galaxies and clusters may show more extreme behaviors due to interactions and stripping, NGC 6503 is undisturbed, which means the signature of dark matter is not masked or distorted. It is, in a sense, dark matter in its purest observed form. In an age where dark matter remains one of the biggest open questions in physics, still undetected directly in any laboratory experiment, galaxies like NGC 6503 remind us that the evidence is already all around us, written in the speeds at which galaxies spin, in the way stars move, and in the shapes that would otherwise make no sense. Though we cannot yet touch it, weigh it, or shine a light on it, we know that it is there, pulling silently in the dark. And in NGC 6503, on the edge of an immense cosmic void, the case is especially compelling. This is not just a galaxy. It is a quiet courtroom where the laws of gravity argue for an invisible presence, and every star in motion is a witness to something unseen yet unmistakably real. Galaxies are often imagined as serene, floating islands of stars, gas, and dust, peaceful structures drifting silently through space. But in reality, the universe can be a violent place. In galaxy clusters and dense regions of the cosmic web, galaxies do not simply drift, they collide, merge, and consume one another in titanic gravitational events. These cosmic encounters are known as galactic mergers, and when a larger galaxy devours a smaller one, astronomers refer to it as galactic cannibalism. But NGC 6503 is different. It is the galaxy that escaped the crowd. Nestled on the very edge of the local void, in a vast region of space that is relatively empty of other galaxies, NGC 6503 has lived a life largely uninterrupted by cosmic violence. In its corner of the universe, there have been no neighboring galaxies to crash into, no tidal arms of distant giants to pull on its stars, and no smaller companions for it to consume. This profound isolation has preserved the galaxy in a way that few others can claim. It is one of the rare systems that appears to have evolved without major mergers, a galactic time capsule, sealed from the chaos of crowded environments. In the denser filaments of the universe, galactic mergers are common and dramatic. When two galaxies collide, their stars generally pass by one another without direct contact, but their gravitational interactions are immense. Gas clouds are compressed, triggering intense starbursts. Stellar orbits are thrown into disarray. Disks are destroyed, bulges built, and black holes sometimes merge in colossal outbursts. The final result is often a new galaxy with a completely different structure, chemistry, and motion than its progenitors. This is how elliptical galaxies are often formed, from the remnants of spirals torn apart in mergers. In contrast, NGC 6503's structure shows none of the typical scars of such events. Its disk is intact, its spiral arms coherent, and its rotation orderly. There are no large tidal streams of stars, no long ribbons of debris that would suggest a recent meal. Its metallicity gradient remains clean and predictable, with no sudden jumps that would indicate the mixing of stellar populations from a recent merger. Its central region shows no sign of a recent inflow of stars or gas that would disrupt its calm profile. The galaxy's star formation history, too, tells a tale of peace. Galaxies that undergo mergers often experience dramatic, temporary spikes in star formation as gas is driven toward the center and compressed. These bursts leave behind telltale signs, dense star clusters, irregular patches of young stars, or extremely bright regions dominated by short-lived massive stars. But in NGC 6503, the pace of star formation appears to have been steady and moderate, without the kind of abrupt changes associated with merger-induced starbursts. Additionally, NGC 6503's kinematics, the way stars and gas move, offer further proof of its undisturbed life. Galaxies that have recently undergone mergers often display complex velocity fields, including warped disks, counter-rotating cores, or disrupted rotation curves. NGC 6503, on the other hand, maintains a smooth, symmetric rotation, with only minor irregularities that can be attributed to internal processes like bar instabilities or density waves. This stability points to a history of evolution governed by internal mechanisms rather than external disruption. Its location on the fringes of the local group, and more importantly on the edge of the local void, is key to understanding how this peaceful history came to be. In the early universe, galaxies formed in areas where dark matter halos overlapped, pulling in baryonic matter to form stars. In denser regions, these halos merged frequently, leading to early and frequent galactic collisions. But in voids, these enormous underdense regions, dark matter halos were fewer and farther between. Galaxies like NGC 6503, forming in such environments, had fewer neighbors to interact with. As a result, they were spared the fates of their cluster-dwelling cousins. In fact, this very isolation allows astronomers to study galactic secular evolution, the slow, internal transformation of galaxies driven not by collisions but by internal dynamics like bar formation, spiral density waves, and gas recycling. NGC 6503 may still exhibit features such as a weak central bar, which is typical in isolated spirals. But even this would have formed gradually, over hundreds of millions of years, shaped by the galaxy's own gravity and gas flows rather than any external jolt. This lack of galactic cannibalism doesn't just affect structure, it also impacts NGC 6503's chemical makeup. In interacting galaxies, gas from mergers can dilute or enrich metallicities, depending on the gas composition of the merging systems. But in NGC 6503, the metallicity gradient has likely evolved naturally from the inside out, with no sudden jumps. This allows astronomers to use it as a control case in studying the natural buildup of elements without contamination from other galaxies. Moreover, the absence of past mergers implies that NGC 6503's dark matter halo is likely pristine and undisturbed. In denser regions, halos are often warped or stripped during collisions, but here, the dark halo has likely remained stable, contributing to the well-ordered rotation curve observed today. This gives astronomers a rare chance to study dark matter halos in isolation, providing crucial constraints on theories about how these halos form, evolve, and affect their host galaxies. Even the galaxy's stellar populations reflect its peaceful history. In merger remnants, you often find evidence of complex age distributions, young, metal-poor stars from dwarf companions mingled with old, metal-rich stars from the primary galaxy. In NGC 6503, the age distribution is more coherent and stratified, with older stars near the core and younger stars in the outer spiral arms. This indicates a gradual star formation history, uninterrupted by the influx of alien stellar populations. Of course, this doesn't mean NGC 6503 has never experienced any form of interaction. On cosmic timescales, even isolated galaxies may have absorbed very small satellites, tiny dwarf galaxies that leave minimal imprint. But these interactions are vastly different from the major mergers seen in denser cosmic environments. They do not disrupt the disk or scramble the galaxy structure. If anything, they are more like gentle drizzles than violent thunderstorms. In this sense, NGC 6503 represents a control sample in the cosmic experiment, a galaxy that shows us what spiral galaxy evolution looks like without external chaos. It helps astronomers understand what features of galactic behavior are intrinsic, and which are the result of environmental violence. Without cannibalism to complicate the picture, every detail of the galaxy's structure, chemistry, and motion speaks with greater clarity. This clarity is why NGC 6503 matters. In the tumult of the universe, it is a quiet voice of order. It shows us that a galaxy can grow, evolve, and shine for billions of years without devouring or being devoured. In a cosmos shaped by collisions, it is the rare survivor that has been left alone. And in its solitude, it speaks not of violence, but of patience. Not of destruction, but of endurance. It is a galaxy that chose a different path, one of peace, and because of that, it offers us one of the clearest views into the quiet mechanics of galactic life. To understand where NGC 6503 fits into the broader architecture of our cosmic neighborhood, we must take a step back and consider the structure of space close to home, our local group of galaxies. The local group is a gravitationally bound collection of more than 80 galaxies, including our Milky Way, the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33, along with numerous dwarf companions. It stretches across approximately 10 million light-years of space, and its members are all interacting, orbiting, or gravitating toward one another in a slow cosmic dance. But where does NGC 6503 lie in relation to this local family? The answer is, NGC 6503 is near the local group, but it is not a member of it. This galaxy resides on the very fringe of our local galactic neighborhood, about 17 million light-years away from Earth. That distance places it just beyond the gravitational boundary of the local group, which is typically defined as encompassing galaxies within a radius of about 5 million parsecs, or roughly 16 million light-years. By that measure, NGC 6503 sits just outside this boundary, making it a kind of peripheral observer, close enough to be considered a neighbor but not close enough to be gravitationally bound to the local group's central mass. This distinction may seem subtle, but it's quite important in the cosmic context. Galaxies within the local group are in mutual gravitational interaction. They may orbit each other, be pulled toward common centers of mass, or eventually merge, as is expected to happen between the Milky Way and Andromeda in about 4.5 billion years. These interactions are strong and observable. In contrast, NGC 6503 is dynamically decoupled from these processes. It is not orbiting the local group's core, nor is it gravitationally bound in a long-term way. It's drifting in a different part of space, following a trajectory largely independent from the internal motions of local group members. This near but not part of status gives NGC 6503 a unique role. It becomes a useful reference point, a marker just outside the local group's domain that helps astronomers define the limits of our galactic neighborhood. Just as distant towns help define the edge of a city, galaxies like NGC 6503 help us understand where the gravitational influence of the local group fades into intergalactic independence. Additionally, its position near the edge of the local void enhances this status. NGC 6503 is located at the interface between cosmic structure and emptiness, between the relatively populated local sheet, where the local group resides, and the vast, underdense expanse of the local void. This transitional position is rare and significant. Most galaxies in the universe are found in denser environments, clustered along filaments, or within groups and clusters. NGC 6503's placement allows it to be studied as a representative of isolated edge galaxies, those that straddle the boundary between galactic civilization and cosmic wilderness. It also helps clarify why NGC 6503 has evolved in such an undisturbed manner. Within the local group, galaxies are often interacting, merging, or affected by the gravitational tides of massive neighbors. Dwarf galaxies especially feel these forces. Many have been stripped of their gas or warped by tidal forces. But NGC 6503, by floating just beyond that sphere of influence, has been spared. It's like a traveler who chose to settle just outside the city limits, free from the bustle and drama inside. Despite being just outside the local group, NGC 6503 is often mentioned in proximity studies because of its relative closeness. In cosmic terms, 17 million light-years is still quite nearby, well within what astronomers call the local volume, a sphere extending out to about 13 million light-years around Earth. This region is rich with data, with many galaxies close enough to be studied in great detail. Because NGC 6503 lies at the edge of this volume, and of the local void, it serves as a boundary case in many galactic surveys. It defines the outer shell of detailed mapping efforts and provides contrast to the gravitationally bound systems inside. There has also been historical debate over whether NGC 6503 might belong to a loose group of galaxies in its own right. Some catalogs suggest it is part of a small association or filament extending along the edge of the local void, including other isolated or semi-isolated systems. However, these associations are much looser than the tightly bound local group. They are not gravitationally cohesive units, but rather spatial groupings without the strong internal gravity needed to bind them together over time. This has important implications for NGC 6503's future. While local group galaxies are on a collision course with one another, especially the Milky Way and Andromeda, NGC 6503 will likely continue its solitary journey, unaffected by those events. Unless pulled into another structure or perturbed by an as yet unseen nearby mass, it may drift further from the local group over cosmic time, carried along by the expansion of space itself. Its future is one of continued isolation, a quiet trajectory through the thinning cosmic web. Ultimately, NGC 6503's place outside, but near, the local group makes it a valuable galactic benchmark. It allows us to observe the contrast between galaxies evolving in close proximity and those developing alone. It helps define the edges of gravitational influence, offers a calm baseline for galactic evolution studies, and provides a boundary marker for the local void itself. It stands not at the heart of our galactic family, but just outside the gates, close enough to study, distant enough to remain untouched. In this role, it becomes a cosmic sentinel. Watching. Orbiting nothing. Alone, but not forgotten. A galaxy on the edge, and by standing on that edge, offering us a clearer view of the universe's larger structures, interactions, and boundaries. To truly appreciate what makes NGC 6503 so special, it helps to compare it with a galaxy we know intimately, our own Milky Way. Both are spiral galaxies. Both possess central bulges and sweeping arms. And both are shaped by the same fundamental physical laws governing gravity, star formation, and cosmic evolution. But despite these broad similarities, NGC 6503 and the Milky Way are vastly different in scale, environment, and cosmic experience. It's like comparing a serene coastal town with a bustling metropolitan capital. One is quiet and remote, the other teeming with interactions and complexity. Together, their differences highlight how environment and mass can shape a galaxy's life. First, consider size. The Milky Way is a giant spiral galaxy, measuring about 100,000 to 120,000 light-years in diameter, depending on how far out you measure its extended halo. It contains an estimated 200 to 400 billion stars, along with massive amounts of gas, dust, and dark matter. By contrast, NGC 6503 is a dwarf spiral galaxy, with a diameter of roughly 30,000 light-years, only about a third the size of the Milky Way. Its total stellar population is dramatically smaller, with only a few billion stars at most, and its overall mass is estimated to be less than one-tenth that of the Milky Way. Yet despite its smaller stature, NGC 6503 is remarkably well-formed. It boasts a central bulge, visible spiral arms, a star-forming disk, and even subtle structural elements like a weak bar, features often associated with larger galaxies. This makes it something of a cosmic overachiever among dwarf spirals. While many small galaxies appear irregular or distorted, NGC 6503 has maintained a crisp spiral identity, thanks in part to its isolation. And this is where the most striking contrast emerges, not in size or shape, but in cosmic surroundings. The Milky Way lives in a crowded neighborhood, nestled within the local group. It has two large galactic siblings, Andromeda, M31, and Triangulum, M33, and is surrounded by dozens of smaller satellite galaxies, such as the Large and Small Magellanic Clouds, the Sagittarius Dwarf Galaxy, and the Canis Major Overdensity. These satellites constantly interact with the Milky Way, creating tidal streams, warps, and dynamic gravitational effects that shape the galaxy's structure over time. NGC 6503, by contrast, is profoundly alone. It lies on the edge of the local void, in a region almost completely devoid of neighboring galaxies. This solitude means that NGC 6503 has never experienced the kinds of major mergers or gravitational tug-of-war events that define the Milky Way's recent history. The Milky Way has been a cannibal, consuming several smaller galaxies in the past few billion years. Streams of stars from these devoured galaxies still linger in its halo, and their remnants continue to inform studies of galaxy formation. But NGC 6503 has no such scars. Its spiral arms haven't been torn or reshaped by encounters. Its halo hasn't been enriched by foreign stars. Its story is one of internal evolution, not external disruption. Even the structure of the galactic disk shows how environment influences development. The Milky Way's disk is warped, likely due to gravitational interactions with its satellite galaxies and possibly the influence of dark matter substructure. It also hosts multiple spiral arms, whose shape and strength are still debated but are undoubtedly influenced by the galaxy's complex surroundings. NGC 6503, on the other hand, features a more flocculent or patchy spiral structure, less grand in design but also less disturbed. This difference reflects how gravity from neighbors can sculpt a galaxy's outer disk into waves and ripples, while isolation often preserves a simpler, unperturbed pattern. There's also a stark contrast in star formation activity. While the Milky Way has regions like the Orion Arm that are actively forming stars, its overall star formation rate is relatively moderate, estimated at about 1 to 2 solar masses per year. NGC 6503, despite its smaller mass, still shows robust star formation, especially in its outer arms, where blue star clusters and emission nebulae indicate the birth of new stars. This continued activity in such a low-density region raises interesting questions. Where does it get the gas? Has it retained its primordial reservoir more effectively due to lack of mergers? These are the kinds of mysteries NGC 6503 helps to explore. The presence, or rather the absence, of a central supermassive black hole also sets the two galaxies apart. The Milky Way hosts Sagittarius A, a black hole with a mass of about 4 million suns, anchoring the very heart of the galaxy. This central giant shapes the motion of nearby stars and likely plays a role in regulating star formation. NGC 6503, on the other hand, shows no evidence of a supermassive black hole, at least not one of significant mass. If it exists, it must be small, perhaps a few 100,000 solar masses or less. This absence may be tied to its evolutionary path, suggesting that massive black holes form more readily in denser environments, or more massive systems. Dark matter halos offer yet another point of comparison. Both the Milky Way and NGC 6503 are surrounded by invisible halos of dark matter, but again, scale matters. The Milky Way's halo may extend hundreds of thousands of light-years and contain up to 90% of its total mass. NGC 6503's halo is similarly dominant but much more compact. What's interesting is that the shape of NGC 6503's rotation curve, which remains flat well beyond the visible disk, is nearly identical to that of the Milky Way, reinforcing the idea that dark matter behaves consistently across scales. The difference lies not in the pattern, but in the magnitude. Finally, when comparing the two galaxies, we can look at their places in the cosmic web. The Milky Way is part of a supercluster complex, the Laniakea supercluster, connected by filaments of galaxies and clusters. NGC 6503 lies on the edge of this same structure but leans outward into the void, closer to emptiness than to density. It is a galaxy on the boundary, looking inward toward the tangle of galaxies like the Milky Way, but also outward into the quiet, dark vastness of the local void. In this sense, NGC 6503 provides a unique perspective, both physically and metaphorically, on what it means to be part of a structure, and what it means to evolve in solitude. So while the Milky Way and NGC 6503 may share the label of spiral galaxy, they represent two very different paths. One is massive, busy, shaped by countless interactions. The other is modest, isolated, and unbothered. One is the product of mergers, growth, and gravitational complexity. The other is the result of quiet, patient self-assembly. And perhaps that's what makes NGC 6503 so compelling. In a universe where interactions dominate, where galaxies often form through collision and chaos, here is one that grew by being left alone. A cosmic hermit, a galactic minimalist, a spiral born not of violence but of time. When we imagine the universe, it's tempting to picture a vast expanse filled evenly with stars and galaxies, a kind of endless ocean where celestial objects float in quiet, uniform distribution. But this vision is profoundly inaccurate. On the largest scales, the universe is not smooth, it is structured. It is woven into an enormous, interconnected network of filaments, sheets, and clusters, all held together by the invisible scaffolding of dark matter. This grand structure is known as the cosmic web, and nestled within its intricate geometry are vast, empty spaces called voids, regions like the one that surrounds NGC 6503. Voids are among the largest features in the universe. The local void, for instance, the vast underdense region on whose edge NGC 6503 resides, is estimated to span around 100 million light-years across. That's a volume so massive that it defies intuitive comprehension. Within it, the density of galaxies drops dramatically, up to 90% fewer galaxies than what we would expect in more average regions of space. And it's not just the number of galaxies that's low. There's less gas, less dust, and less gravitational activity overall. These voids are cosmic deserts, surrounded by the fertile filaments and clusters of the cosmic web. But far from being boring, voids are essential to understanding the structure, evolution, and fate of the universe. They are not empty mistakes or leftovers, they are crucial elements of the cosmic design. In fact, the way matter flows around and out of these voids is a major driver of the large-scale evolution of the cosmos. And galaxies like NGC 6503, which sit on the boundaries of these voids, are our key informants, observers perched at the threshold between emptiness and structure, offering a unique perspective on both. To understand why voids matter, we first need to grasp how the cosmic web forms. In the early universe, tiny quantum fluctuations in the primordial density field, imperceptible ripples in the sea of particles, grew over time under the influence of gravity. Regions that were slightly denser attracted more matter and grew into filaments and clusters, while underdense regions became increasingly depleted, expanding faster than their surroundings and evolving into voids. This dynamic gave rise to a sponge-like architecture, the cosmic web, where galaxies are concentrated along the filaments and walls, and voids are the bubbles in between. voids expand over time because they contain less gravitational mass. While clusters and filaments pull matter inward, voids do the opposite. They push matter outward. This difference in behavior means that voids become larger and emptier as the universe ages. Their expansion is accelerated by dark energy, the mysterious force driving the overall cosmic expansion. In fact, the cleanest environments in which to study dark energy's effects are these very voids. By measuring how fast voids expand or how galaxies move near their edges, astronomers can test predictions about cosmic acceleration and probe the nature of dark energy with a precision difficult to achieve in denser regions. NGC 6503's position on the edge of the local void makes it especially valuable for such studies. It exists in what's called a void wall, the transition zone between the emptiness of the void and the relative richness of the surrounding cosmic web. Galaxies in these wall regions experience different dynamics than those in either deep voids or dense clusters. They feel weaker gravitational tugs from nearby galaxies and filaments, and they are often aligned along large-scale flows of matter moving outward from voids. Studying these galaxies helps scientists map the velocity fields around voids, how matter is moving in and out of these regions, and understand the overall mass distribution of the universe. Moreover, void galaxies like NGC 6503 tend to evolve in isolation, untouched by the frequent collisions and interactions that shape galaxies in denser areas. This makes them natural laboratories for studying intrinsic galactic evolution. In more crowded environments, it's hard to disentangle internal processes from external influences. Did a galaxy's bar form because of internal dynamics or because of a past merger? Are its gas reserves depleted because of internal star formation or because another galaxy stripped it away? In a void-edge galaxy like NGC 6503, the absence of interference provides a clearer view of a galaxy's natural behavior. Another reason voids matter is their role in challenging and refining cosmological models. Different theories of gravity and dark energy predict slightly different behaviors in underdense regions. For example, alternative gravity theories such as modified Newtonian dynamics, MOND, or F.R. gravity make distinct predictions about how galaxies move in voids versus in clusters. Precise observations of galaxies like NGC 6503, tracking their velocities, structures, and dynamics, can help rule out or support these competing models. In this way, a single galaxy near a void can provide data that resonates across all of cosmology. Furthermore, voids act as clean testing grounds for detecting large-scale anomalies or non-uniformities in the universe. The standard cosmological model assumes that the universe is homogeneous and isotropic on the largest scales. That is, it looks roughly the same in all directions and from all locations. But what if that's not entirely true? What if there are large-scale flows, asymmetries, or structures that violate this principle? Galaxies near voids, especially isolated ones like NGC 6503, can be used to test these assumptions with less contamination from local group dynamics or cluster effects. Even in galaxy formation models, voids provide key counterpoints. While dense environments are known to nurture elliptical galaxies and quench systems, those with little or no star formation, void environments tend to harbor bluer, gas-rich spiral galaxies, like NGC 6503. These galaxies tend to retain their gas longer, form stars more steadily, and maintain disk structures for extended periods. This contrast helps astronomers piece together the environmental dependence of galaxy evolution, showing how location within the cosmic web can influence a galaxy's fate just as much as its internal mass and composition. And let's not forget the philosophical dimension. Voids are the dark threads between the stars, the negative spaces that give the cosmic web its shape. They are reminders that absence is just as important as presence, that emptiness can define structure, and that silence, cosmic silence, can still carry profound meaning. NGC 6503 sits not just near a void, but on the threshold of understanding, between what we see and what we wonder, between structure and the abyss. So when astronomers peer into the surroundings of this modest galaxy, they are not just looking at a local curiosity. They are studying the shape of the universe itself. Every measurement of NGC 6503's motion, Every analysis of its dark matter halo, every mapping of its gas and stars feeds into a larger project, the decoding of the cosmic blueprint, the vast web of structure that stretches across billions of light years, shaped by forces we are only beginning to comprehend. NGC 6503 helps us see that to understand galaxies, we must understand their environment. And to understand the universe, we must study the voids, the great empty spaces that whisper truths in their silence. While NGC 6503 stands out due to its location on the edge of the local void and its well-defined spiral structure, it is far from alone in the broader family of galaxies that inhabit cosmic voids. Across the universe, astronomers have identified a variety of galaxies that exist either deep within voids or along their perimeters, each offering a unique perspective into how isolation shapes galactic evolution. By studying these galaxies and comparing them to one another, a fuller picture of life in the emptiest parts of the cosmos begins to emerge, one that's quieter, slower, and in many ways more pristine than that in crowded clusters and filaments. Void galaxies generally fall into a different evolutionary path than their cluster-bound counterparts. Most notably, they tend to be bluer, more gas-rich, and more actively star-forming. This trend holds across various studies, suggesting that galaxies in voids, despite the lack of external stimulation, often maintain a steady pace of internal activity. This sets them apart from many galaxies in denser regions, where interactions and mergers might quench star formation or trigger dramatic but short-lived starbursts. One of the most well-known examples of a void galaxy is KK246, a dwarf irregular galaxy located deep inside the local void. KK246 is fascinating because it is truly solitary. It resides far from any large galaxy, and even from many smaller ones. It is also notable for its extremely high dark matter content compared to its visible mass, with rotation curves indicating that dark matter dominates its dynamics at almost every radius. This is similar to what we observe in NGC 6503, though KK246 is far less structured. It lacks the well-formed spiral arms or bulge of NGC 6503, instead appearing chaotic and irregular. Its chaotic structure is a common feature of low-mass void galaxies, many of which fail to form the elegant shapes seen in larger, denser galaxies. The lack of tidal forces and interaction can, paradoxically, lead to a lack of organizational momentum. Another interesting void galaxy is UGC 4879, an isolated dwarf spheroidal located in the local volume but far from other major systems. UGC 4879 is nearly gasless and has no significant current star formation, a stark contrast to NGC 6503. This shows that even in voids, not all galaxies are identical. Some have been quiescent for billions of years, perhaps due to a lack of fresh gas in fall, or due to supernova-driven outflows that expelled the material needed for new stars. UGC 4879 shows that star formation history in voids is not uniform, and that other factors, like internal feedback or early interactions, may still influence outcomes, even in these quieter neighborhoods. Then there's VGS_12, a particularly remarkable galaxy studied as part of the Void Galaxy Survey (VGS). Located deep within a void, VGS_12 is a blue, disc-shaped galaxy with an extensive reservoir of neutral hydrogen gas. But what makes it special is that its gas disk is perpendicular to its stellar disk. This suggests that it may have accreted gas directly from the intergalactic medium, unimpeded by interactions or disruptions from nearby galaxies. In a crowded environment, such smooth accretion is rare. Gas is usually stripped away or jostled by gravitational influences. But in voids, galaxies like VGS_12 may slowly siphon cold gas from their surroundings, building their disks and continuing star formation for billions of years. This offers compelling evidence that void galaxies might evolve more purely, with fewer complications introduced by their neighbors. Another galaxy of interest is IC 1101, often cited as one of the largest galaxies in the known universe. While it doesn't reside in a void, it provides a powerful contrast to void galaxies. IC 1101 is a giant elliptical, the kind of massive system that forms from repeated mergers and interactions in the densest cluster environments. Its massive core, extended halo, and low star formation rate are all outcomes of its environment. Compare that to a galaxy like NGC 6503, which retains a spiral structure, moderate size, and active star formation. The contrast between these two kinds of galaxies underscores just how profoundly environment shapes morphology and evolution. Other notable void galaxies include those in the Bodi's void, one of the largest known cosmic voids, spanning over 300 million light-years in diameter. This vast region contains incredibly few galaxies. Less than 60 have been identified in an area that might otherwise contain thousands. Some of these galaxies appear unusually diffuse or elongated, with faint stellar populations. In such extreme isolation, galaxies evolve with very little external pressure, and their structures often reflect that. They may retain large amounts of gas, develop low surface brightness disks, and evolve on extended timescales. Interestingly, a few void galaxies seem to challenge expectations. Some are more massive than anticipated, or show signs of minor interactions, perhaps with tiny dark galaxies or low-mass halos that never formed significant stellar populations. These anomalies prompt researchers to rethink assumptions about how matter is distributed even in the emptiest parts of the universe. They also hint at hidden complexities, like unseen gas flows, ancient interactions, or unaccounted for gravitational structures. What unites void galaxies, despite their diversity in size, structure, and star formation, is their common experience of gravitational solitude. Without tidal fields from neighboring galaxies to warp their disks, without intergalactic gas clouds to shock or compress them, and without frequent mergers to reset their morphology, these galaxies represent a kind of natural laboratory. They are subject to fewer outside variables, which makes them ideal for testing theories about internal processes, how spiral arms form, how bars emerge, how gas settles into rotating disks, and how stars are born from internal instability rather than external pressure. For NGC 6503, the comparison is revealing. While many void galaxies are small, irregular, or quiescent, NGC 6503 stands out for being larger, structured, and still actively forming stars. This may be due to its location on the edge of the void rather than deep inside it. The edge regions may have just enough residual density, just enough proximity to ancient flows of matter, to allow for the formation of a more coherent and mature spiral galaxy. It might have started its life closer to the filaments and slowly drifted outward, or it may be a rare survivor of a sparser filament that failed to fully collapse into a cluster. The broader lesson is clear: voids are not just empty spaces. They are subtle arenas of cosmic evolution, where matter moves at a different pace and galaxies chart unique paths. Studying void galaxies, whether structured like NGC 6503 or irregular like KK246, gives us a critical control group for galactic science. They allow us to ask, what happens to a galaxy when nothing happens to it? When it is left alone for billions of years to grow, spin, shine, and fade on its own terms? These questions are not academic. They are central to understanding how the universe evolves. Because in these empty places, where gravity whispers rather than shouts, we may find the purest expressions of galactic life. In the vast observational theater of the cosmos, astronomers are constantly seeking clean, controlled environments where they can study galactic behavior free from the noise of external interference. But the universe is messy. Most galaxies are entangled in a chaotic ballet, pulling on one another, crashing into one another, flaring with starbursts triggered by gravitational nudges or stripped of their gas by environmental pressure. Finding a galaxy that has evolved in near-perfect solitude is like discovering an untouched artifact in an archaeological site that's been looted for centuries. It's rare, precious, and immensely instructive. In this way, NGC 6503 serves as a kind of cosmic laboratory, a natural experiment in how galaxies evolve without disruption. Because it sits on the edge of the local void, essentially a vacuum compared to the bustling filaments of the cosmic web, NGC 6503 has existed for billions of years with very little gravitational interference from other galaxies. It has not been pulled, twisted, merged, or cannibalized. It hasn't passed through galaxy clusters filled with hot intergalactic plasma that might strip its gas. It hasn't had to fend off flybys from massive neighbors that could torque its disk or warp its spiral arms. It is, in essence, a galaxy in a vacuum chamber, ideal for studying the raw, internal processes that drive galactic evolution. This isolation gives astronomers a unique baseline, a system where they can observe how star formation, disk stability, dark matter interactions, and gas dynamics unfold without external stimuli. For example, in more populated regions of space, a starburst might be triggered by a close encounter with another galaxy. Gas gets compressed by tidal forces, molecular clouds collapse rapidly, and a galaxy might flare into temporary brightness. But in NGC 6503, any star formation that occurs is almost certainly intrinsic, driven by slow internal processes such as gravitational instabilities within the disk or feedback from previous generations of stars. Because of this, astronomers can study how spiral structures maintain themselves in isolation. In many galaxies, the arms are influenced or even caused by interactions. But in NGC 6503, the flocculent nature of its arms, less grand design and more scattered patches, suggests a slower, more organic formation. Without nearby galaxies to induce or reinforce the spiral density waves, the arms must be forming and sustaining themselves through internal instabilities, ripples in the disk caused by differential rotation and local variations in density. The presence of a mild central bar adds to the intrigue. Bars are often associated with angular momentum redistribution, gas funneling, and star formation in central regions. In NGC 6503, the bar appears relatively weak, suggesting it forms slowly and without the kind of violent triggers seen in bar-dominated galaxies inside clusters. Studying such a bar in a quiet environment helps model the timescales and dynamics of bar formation in isolation, a process still not fully understood. The galaxy's rotation curve, which shows flatness at large radii, reveals the presence of dark matter. In denser regions, this signature can be clouded by tidal distortions or confusion with gravitational interactions. But in NGC 6503, the rotation is clean, undisturbed, making it a textbook example of how dark matter influences galaxy dynamics. This allows scientists to refine their models of dark matter halos, particularly in dwarf spirals, where baryonic matter contributes less to the overall gravitational profile. The lack of a supermassive black hole further simplifies this analysis, removing a complex gravitational variable from the galactic center and making the rotation curve even easier to interpret. Another area of research that benefits from NGC 6503's isolation is the study of gas content and distribution. With no surrounding galaxies to siphon gas or compress the disk, any gas within NGC 6503 must be primordial or accreted smoothly from the intergalactic medium. Mapping its neutral hydrogen using radio observations gives a near-pristine look at how gas settles into a stable disk, how it rotates, how it fuels star formation, and how it may slowly evolve over cosmic time. These observations contribute to broader questions like, how does a galaxy retain its gas? How long can it sustain star formation at a given rate? And how do these properties change as a galaxy ages? What's especially fascinating is that NGC 6503 appears to have avoided the quenching processes that shut down star formation in many galaxies. It has gas. It has active star-forming regions. And it has done this not through dramatic bursts or rapid recycling, but through gradual, steady accumulation and consumption of fuel. That is, in many ways, the purest form of star formation, a galaxy quietly converting hydrogen into starlight, uninterrupted for billions of years. It becomes a kind of control sample in galactic astrophysics. When we want to understand how a galaxy behaves without the influences of stripping, harassment, or merger activity, we can look to NGC 6503. Its stellar population gradients, from hot, young, blue stars in the outer arms to older, redder stars in the central regions, further reflect this undisturbed history. The galaxy has been free to build its stellar architecture from the inside out, creating a clean stratification of populations based on age and metallicity. This kind of stratification is often disrupted in more interactive systems, where mergers and encounters mix populations and inject new starbursts into older regions. But in NGC 6503, the layers remain largely intact, offering a cross-section of galactic time, preserved in stellar light. Even the lack of companions becomes a data point. Many galaxy evolution simulations must include substructure, smaller satellite galaxies or dark matter clumps that can gravitationally influence the primary disk. NGC 6503 doesn't appear to have significant companions or even nearby luminous galaxies. Its solitary nature allows for modeling its evolution using just a single dominant gravitational source, ideal for simulations that require minimal variables. It's the perfect testbed for simplified galactic models, tools that can then be applied to more complex systems. Its location at the edge of a void also makes it an important reference point for large-scale structure studies. As galaxies drift outward from voids due to gravitational repulsion and cosmic expansion, their velocities, alignments, and morphologies may show subtle trends. Studying many galaxies in this transitional zone, including NGC 6503, helps astronomers understand how void environments influence galaxy spin directions, orientations, and even minor anisotropies in their distributions. These metrics feed directly into cosmological models and simulations, helping refine our understanding of how galaxies and voids co-evolve. In the end, NGC 6503 is more than just a lonely galaxy. It's an ideal case study, a laboratory suspended in the vacuum of space. It shows us what a galaxy can be when left to its own devices. It offers answers to some of the most fundamental questions about galactic behavior: how disks form and evolve, how gas turns into stars without triggers, how structure arises from gravity alone, and how dark matter halos quietly shape the dance of visible matter. It is, in every sense, a benchmark, against which we can measure the noise and confusion of other galaxies and peel back the layers of interaction to find the underlying physics beneath. In the stillness of NGC 6503, we hear the quiet voice of the universe, speaking not through collision or violence, but through stability, patience, and time. Despite the prevailing narrative that NGC 6503 has lived a life of solitude, spinning alone on the edge of the local void, astronomers cannot entirely rule out the possibility of past interactions. In fact, within its quiet demeanor lie subtle clues, faint whispers in the light and structure of the galaxy, that invite deeper inquiry into whether it truly has always been alone, or if long ago, it brushed against a fellow traveler in the dark. One of the first reasons scientists might consider a past interaction, even in a galaxy like NGC 6503, is that absolute isolation is incredibly rare in a dynamic universe shaped by gravity. Cosmic structures evolved from dense patches of matter that drew gas, stars, and dark matter inward over billions of years. The idea that a galaxy could remain entirely untouched since its formation is difficult to reconcile with simulations of the early universe. Even galaxies that currently reside in voids or along their edges likely originated in denser regions, only to drift outward over cosmic time as gravitational flows pushed matter away from expanding voids. This migration process opens the door to a history that was not always solitary. So what signs might suggest a past interaction for NGC 6503? Astronomers look at several specific features. First, the morphology of the galaxy. NGC 6503 is a dwarf spiral, and while its overall structure is intact and symmetrical, it does possess a weak bar structure, a linear feature extending from the central bulge and running through the disk. Bars can form through internal processes, especially in isolated galaxies, but they can also be triggered or strengthened by tidal interactions, particularly if another galaxy passes close enough to disrupt the angular momentum of stars in the inner disk. While NGC 6503's bar is subtle, it might hint at some minor gravitational stirring in its past. Another feature of interest is the asymmetry in its spiral arms. Unlike grand design spirals such as M51 or NGC 1300, which exhibit symmetrical, well-defined arms, NGC 6503 displays more flocculent or patchy arms, with uneven brightness and curvature. This can be a sign of internal turbulence and irregular star formation, but it may also reflect the lingering influence of a disturbance long past, perhaps a flyby encounter with a smaller satellite galaxy that never fully merged. These kinds of interactions, especially with dwarf companions, are notoriously difficult to detect after the fact, as the smaller galaxy may have been entirely assimilated or disrupted into invisibility. Astronomers also examine the distribution of gas within the galaxy. Neutral hydrogen, HI, observations of NGC 6503 reveal an extended disk of gas that rotates regularly but shows slight warps or deviations at the outer edges. In many galaxies, such warps are caused by tidal torques from external companions. In an isolated galaxy, these features could instead be attributed to internal disk instabilities or slow, uneven accretion of intergalactic gas. However, the mere presence of irregularities suggests that the galaxy's history may not be as tranquil as its current environment implies. Then there is the possibility of fossil evidence, stellar streams or tidal tails that sometimes persist long after a merger or interaction. In more massive galaxies, such features are often easier to detect, as the absorbed companion leaves behind luminous trails of stars that wrap around the host like cosmic fingerprints. In smaller systems like NGC 6503, any former companions would have been less massive and more fragile, and their debris might now be thoroughly blended into the stellar halo or disk. This makes detection extremely difficult, especially without ultra-deep imaging or kinematic surveys that can identify subtle differences in stellar motion or composition. While no such clear tidal features have yet been observed in NGC 6503, the absence of evidence is not necessarily evidence of absence. It's entirely possible that in the distant past, perhaps billions of years ago, NGC 6503 experienced a minor merger or interaction that seeded its current morphology. Any disturbances may have since relaxed, and the galaxy could have settled back into a symmetrical shape, especially in the absence of subsequent interactions that might have compounded the damage. It's also worth considering the galaxy's migration history. NGC 6503 may not have been born exactly where it is now. Over billions of years, galaxies move along gravitational gradients shaped by the mass distribution of the universe. If NGC 6503 once resided closer to denser regions, near the edge of a filament, or a small group, it may have encountered other galaxies in its youth, then drifted out toward the void as the local void expanded. This process would naturally reduce the likelihood of interactions in recent epochs but allow for earlier contact in its formative period. Supporting this idea is the fact that NGC 6503 appears to be well-formed. Its spiral disk is organized, its star formation ongoing, and its structure coherent. If it were truly primordial and untouched, one might expect a less developed system, perhaps an irregular dwarf, or a diffuse low-surface brightness galaxy. But NGC 6503 displays enough maturity and internal structure to suggest that it may have experienced formative events, including mergers or accretion episodes that helped build its mass and trigger internal instabilities. Another speculative but plausible scenario involves the ingestion of dark satellites, small dark matter halos with little to no luminous matter. These objects could perturb NGC 6503 gravitationally without leaving behind a trail of stars. While difficult to detect directly, the presence of such satellites might explain mild asymmetries in rotation curves or stellar distribution. If this occurred in the past, it could account for morphological anomalies without requiring a visible intruder. Ultimately, the question of whether NGC 6503 has experienced past interactions is still open-ended. Its current state suggests isolation, but the cosmos is a long game. Even a single event, billions of years ago, could leave faint traces detectable only with the most sensitive instruments and methods. In the absence of smoking gun evidence, astronomers rely on statistical modeling, simulations, and comparison with other similar galaxies to build a likely history. Whether it had companions that have since vanished, or whether it danced alone from the start, NGC 6503 remains a powerful reference point. Its very ambiguity is instructive. It reminds us that even in solitude, galaxies are shaped by time, by environment, and by the unseen flows of dark matter and gas. Its serenity may be real, or it may be the quiet that follows a long-ago whisper of cosmic contact. To fully understand a galaxy, it's not enough to look at its stars. In fact, some of the most revealing insights into a galaxy's history, structure, and future come not from visible light at all, but from the cold, invisible reservoirs of hydrogen gas that surround and thread through its disk. Neutral hydrogen, often abbreviated as HI, is the raw material from which stars are born. And when astronomers peer into galaxies using radio telescopes tuned to the 21 centimeter line, they can map this neutral hydrogen in extraordinary detail, painting a picture of the galaxy's structure and behavior that's otherwise hidden to optical instruments. For NGC 6503, this kind of HI gas mapping has proven invaluable. Despite its relative isolation and modest size, the galaxy possesses a surprisingly rich envelope of neutral hydrogen. This is somewhat expected for a dwarf spiral like NGC 6503, which hasn't undergone disruptive mergers or environmental stripping that would have depleted its gas content. Yet it's the distribution and motion of that hydrogen that offer some of the most tantalizing clues about the galaxy's evolution and composition. Radio observations using instruments like the Very Large Array, VLA, in New Mexico and single-dish radio telescopes such as the Green Bank Telescope, GBT, or the Westerbork Synthesis Radio Telescope in the Netherlands have been able to trace the HI gas across and beyond the visible extent of NGC 6503. These studies reveal that its hydrogen disk extends well beyond the optical disk, often by a factor of 2 or more. While the bright stars of the galaxy may span around 30,000 light-years, the HI disk can reach out 50,000 light-years or farther, forming a vast, faint halo of raw material that envelopes the entire structure. This extended HI disk is important for several reasons. First, it confirms that NGC 6503 is actively feeding its star formation, not through external gas infall from companions, as none are visible, but likely through a gradual cooling and condensation of its own halo gas, or possibly through accretion of intergalactic hydrogen left over from the early universe. Its position on the edge of the local void might even enhance its ability to access pristine cosmic gas that has not yet been processed by other galaxies. Second, HI mapping reveals the kinematics of the galaxy, how gas moves within the gravitational potential well. By tracking the Doppler shifts of the 21 centimeters line across different parts of the galaxy, astronomers can construct highly detailed rotation curves. For NGC 6503, these curves show a smooth, flat profile at large radii, meaning the velocity of rotation doesn't decline as one moves outward from the center. This is strong evidence for the presence of a dark matter halo, which contributes extra gravitational pull in the galaxy's outskirts, preventing the gas and stars from flying apart. Interestingly, the gas itself is not perfectly symmetrical. While the inner rotation is quite regular, studies have found slight warping in the outer HI disk. This warp could be the result of past minor interactions, accretion from misaligned gas streams, or internal dynamical processes within the disk. In an isolated galaxy like NGC 6503, the persistence of such a warp may reflect a very long relaxation time, since there are no external forces acting to restabilize or perturb it further. These small warps are valuable diagnostics of galactic history, often acting like fingerprints left behind by past events that no longer leave more obvious evidence. Radio observations also help identify HI surface density thresholds, critical values beyond which the gas is dense enough to form molecular hydrogen, H2, the immediate precursor to star formation. In NGC 6503, the inner disk appears to sustain densities high enough to trigger active star formation, which is corroborated by ultraviolet and H-alpha emission that trace young, hot stars. But farther out, the HI thins into diffuse halos where star formation is no longer efficient. This density gradient helps astronomers understand the self-regulation of galactic disks, how gas inflows, rotation, and stellar feedback work in concert to manage the birth of stars across different galactic zones. There's also a notable absence of high-velocity clouds, HVCs, or anomalous gas streams, which are sometimes found in galaxies with histories of interaction or gas accretion. This supports the case for long-term isolation, reinforcing the idea that NGC 6503 has not experienced recent mergers or significant disturbances. Its HI profile is clean, with a symmetric velocity field, well-defined major and minor axes, and no signs of gaseous inflows or outflows of the kind often seen in more tumultuous galaxies. Another fascinating result from HI mapping is the thickness of the gas disk. In many spiral galaxies, especially those with active bars or bulges, the HI can become vertically extended due to heating from star formation or gravitational instabilities. NGC 6503, by contrast, shows signs of a relatively thin HI disk, at least in its midplane. This suggests a stable, rotationally supported disk that has not been disrupted vertically by internal shocks or external perturbations. Such stability is rare and makes the galaxy an ideal subject for modeling galactic disk equilibrium. Recent studies have also combined HI data with observations across other wavelengths, CO lines for molecular gas, H-alpha for star-forming regions, and UV for young stellar populations, to create a full multi-phase map of NGC 6503's interstellar medium. These composite maps help trace the life cycle of gas, from diffuse HI to dense molecular clouds to newborn stars. And because the galaxy is so undisturbed, these transitions can be modeled in clean conditions, free from the confusion of overlapping sources or turbulent histories. Moreover, the HI data allows researchers to estimate the total gas mass of the galaxy. NGC 6503's neutral hydrogen content is estimated to be on the order of several hundred million solar masses, a significant reservoir for a galaxy of its size. This gas, if used efficiently, could sustain star formation for several more billion years, suggesting that the galaxy is still in the middle of its life cycle, with much evolution yet to come. Finally, the presence of such a well-defined HI structure in an isolated dwarf spiral reinforces a broader truth about galaxies in void environments. Isolation does not mean stagnation. On the contrary, NGC 6503 shows that even in the absence of interaction, galaxies can remain dynamic, self-sustaining systems. They evolve not through collisions or chaos, but through a slow, inward spiral of gravity, cooling, and star formation. HI mapping captures this elegant balance between structure and fluidity, and in NGC 6503, it offers a model example of galactic calm, an island in space, surrounded by silence, yet humming with quiet energy. Speculating about the distant future of NGC 6503 is like casting one's eyes across a dark sea, watching a solitary ship drift silently toward the edge of a horizon we cannot fully see. Today, the galaxy rests in near total solitude on the boundary of the local void, untouched by the gravitational bustle that defines so many of its galactic peers. But what lies ahead for a galaxy that lives on the outskirts of the cosmic web? Will NGC 6503 remain forever isolated, spinning quietly in a vast darkness? Or is its fate ultimately tied to the larger, shifting structures of the universe? To answer that, we must first consider the cosmic context. NGC 6503 resides on the outer rim of the local void, a region more than 100 million light-years across that contains remarkably few galaxies. This part of space is underdense, meaning it exerts less gravitational pull compared to more crowded regions of the universe. Matter naturally flows from voids toward denser filaments and clusters, much like water running downhill. But NGC 6503 is positioned not inside the deepest part of the void, but along its edge, just close enough to still be part of the larger cosmic structure, yet far enough to be largely unaffected by other galaxies. This placement gives it a degree of gravitational freedom that most galaxies never experience. Over the next few billion years, barring any unexpected encounters, NGC 6503 will likely continue as it has for eons, rotating, forming stars, and slowly aging. Its hydrogen reserves, while finite, are sufficient to fuel star formation for billions more years. Unless an external force intervenes, it will transition naturally from a gas-rich, star-forming spiral to a more quiescent system, a dwarf spiral gradually winding down, its bright blue stars fading into golden hues as star formation declines. Its continued isolation supports this evolutionary arc. In dense galactic environments, interactions, mergers, and gas stripping can rapidly change a galaxy's destiny. But for NGC 6503, evolution proceeds on internal time, not driven by collisions but by the slow consumption of its own fuel. Star by star, it will convert hydrogen into heavier elements, enriching its interstellar medium and steadily populating its disk with older, redder stars. But cosmic isolation is not necessarily a permanent condition. The universe is expanding, but not uniformly. The local void is not static, it is expanding faster than average due to its low matter content, effectively pushing galaxies away from it. NGC 6503, being on the edge of this void, experiences a kind of gravitational repulsion from the underdense region behind it, and a subtle attraction toward the higher density regions in the opposite direction. This leads to what cosmologists call a peculiar velocity, a motion not caused by the general expansion of the universe, but by local gravitational imbalances. Studies suggest that galaxies on the periphery of the local void, including NGC 6503, may be slowly drifting away from the void's center, pulled gently toward nearby overdensities. In NGC 6503's case, this could mean a slow movement toward the outer edges of the local group or beyond, possibly even toward the Virgo supercluster, which dominates our broader cosmic neighborhood. However, these motions are extremely slow on human timescales. Even over billions of years, the change in NGC 6503's position relative to other galaxies would be minimal, unless significant gravitational events occur. But what of those possibilities? Could NGC 6503 eventually encounter another galaxy? While it seems unlikely in the short term, the distant future of the universe spans such unfathomable timeframes that even low-probability events can become almost inevitable. If NGC 6503 continues on a path toward higher-density regions, billions or even trillions of years from now, it may be drawn into larger galactic structures. However, there's a significant counterpoint to this: the accelerating expansion of the universe. Driven by dark energy, the universe is not just expanding, it's accelerating. Over time, galaxies not gravitationally bound to one another will be flung apart by this expansion, effectively isolating themselves from each other forever. If NGC 6503 is not gravitationally tied to any neighboring galaxy, and if no strong attractor lies close enough to overcome this expansion, then it may become eternally stranded, a lone ember adrift in an ever-cooling cosmos. Eventually, the observable universe will shrink, as the expansion pushes galaxies beyond the cosmological event horizon. NGC 6503 may become invisible to future observers from the Milky Way or anywhere else. From within its own disk, intelligent beings, if they exist, might see only their own galaxy, suspended in a void of absolute blackness, with no clues to the grandeur that once surrounded them. Looking even further ahead, into the far future of cosmic evolution, the stars of NGC 6503 will gradually die. The bright, short-lived blue stars will vanish first, followed by yellow and red main sequence stars. Over trillions of years, the galaxy will dim, evolving into a galactic graveyard filled with white dwarfs, neutron stars, and black holes. Without new gas inflow or interactions to reignite star formation, NGC 6503 will become a quiet fossil of a once luminous spiral, still orbiting its dark matter halo but producing no new light. And yet, even in that far future darkness, its story will matter. NGC 6503, if preserved in its current state, will carry within its stars and structure the entire fossil record of a galaxy that evolved alone, a pristine example of how galaxies can live and die when untouched by cosmic conflict. For future civilizations or advanced astronomers, it could be a time capsule of galactic purity, an echo of the conditions that defined the early universe and the nature of dark matter. Speculation also opens the door to more imaginative possibilities. Could NGC 6503 ever be redirected by a massive gravitational event, such as a rogue galaxy wandering near enough to alter its trajectory? Could dark matter substructures, unseen and unexpected, gradually exert influence over cosmic timescales? Might the galaxy one day experience an unexpected inflow of intergalactic gas, reigniting star formation and altering its fate? These are unknowable answers, shaped by processes too slow and vast for current science to resolve. But what we can say with certainty is that NGC 6503's fate, at least for now, appears to be one of solitude, slow transformation, and endurance. Barring cosmic surprises, it will continue to orbit quietly at the edge of the local void, spinning silently in the darkness, forming stars as long as it can, and then fading softly into the future. It will remain a symbol of what a galaxy can become, not by conflict, but by quiet perseverance. From a scientific perspective, NGC 6503 may seem like just another small spiral galaxy, quietly rotating on the outskirts of the observable galactic tapestry. But in truth, this unassuming dwarf spiral has become a treasure trove for astronomers, a kind of controlled experiment conducted by nature itself. What it teaches us is not loud or explosive. It is quiet, deliberate, and incredibly valuable. In its stillness, its solitude, and its structural integrity, NGC 6503 allows astronomers to distill the essential mechanics of galaxy formation and evolution, free from the noise and chaos that confound observations of more crowded galactic environments. One of the primary lessons it offers is about galactic evolution in isolation. Most galaxies in the universe are shaped, distorted, or even destroyed through interactions with neighbors. In galaxy clusters and dense groups, tidal forces, mergers, and gas stripping events are common. These make it difficult to isolate internal processes from external triggers. NGC 6503, perched quietly on the edge of the local void, evolves largely without interference. It provides a rare example of a galaxy that can be studied in near-perfect gravitational solitude, an opportunity to see how a spiral galaxy can build and maintain itself without major disturbances. This setting allows researchers to study the intrinsic behavior of galactic disks, including how stars form, how spiral structures emerge, and how matter organizes itself under the influence of gravity and dark matter. Because there's no significant history of major collisions or mergers, its spiral arms, central bulge, and bar structure have all likely developed internally. This offers a clearer picture of how secular processes, such as disk instabilities, angular momentum redistribution, and feedback from stellar winds, sculpt galaxies over time. NGC 6503 is also instrumental in improving our understanding of dark matter distribution. Its clean, flat rotation curve, measured far into its outer regions through HI gas mapping, strongly indicates the presence of a dark matter halo. In more complex systems, interactions and chaotic gravitational forces can obscure or complicate such readings. But here, the lack of interference allows astronomers to derive precise dark matter profiles and compare them to simulations. This has implications for everything from the cold dark matter paradigm to the behavior of dark matter in low-mass galaxies. Its status as a dwarf spiral further expands our knowledge of galactic diversity. Dwarf galaxies often fall into irregular or elliptical categories, especially when shaped by external forces. But NGC 6503 shows that small galaxies can maintain structured, rotating disks over billions of years if left undisturbed. This challenges certain models of galaxy formation that assume low-mass galaxies cannot sustain orderly morphologies without external influences. NGC 6503 tells us otherwise. With enough mass and stability, a dwarf spiral can be a beautifully formed, long-lived object, even in isolation. Another insight lies in the chemical and stellar population gradients that NGC 6503 displays. Without the mixing effects of mergers, astronomers can more cleanly measure how metals, elements heavier than hydrogen and helium, are distributed across the galaxy. These gradients reveal the history of star formation and gas accretion in different regions, and help calibrate chemical evolution models that predict how galaxies enrich themselves over time. In more chaotic galaxies, these gradients are smeared or reset by interactions. But here, the gradual buildup of stars has left behind a layered fossil record that can be studied in pristine condition. Its extended HI gas disk, mapped in radio frequencies, offers a case study in how gas reservoirs behave in galaxies that are free from ram pressure stripping, tidal interactions, or other environmental disturbances. This helps researchers understand the balance between gas inflow, consumption via star formation, and the outflow of material from stellar feedback. The observed gas dynamics provide a near-perfect baseline against which to compare more complicated systems. Essentially, it gives scientists a before and after framework, NGC 6503 as the baseline, and more disturbed galaxies as the modified case. Star formation within the galaxy is another area where NGC 6503 provides clarity. It forms stars at a steady, modest rate, not through bursts triggered by interactions, but via slow internal mechanisms. This kind of ongoing, low-intensity star formation is harder to observe in denser galactic environments, where external triggers dominate. Studying NGC 6503 helps calibrate star formation efficiency, the relationship between gas density and stellar birth rate, and the longevity of star-forming regions in a stable disk. Then there's its potential lack of a central supermassive black hole. In galaxies of comparable size and morphology, it's not uncommon to find evidence of such a black hole, even if it's inactive. But in NGC 6503, evidence for a central black hole is weak or altogether absent. This absence raises questions. Are supermassive black holes less common in isolated galaxies? Do they require mergers and interactions to form and grow? Could NGC 6503 be an example of a galaxy that simply skipped the black hole phase, or one where a black hole remains too small or dormant to detect? Whatever the answer, the galaxy expands our understanding of central mass concentrations and their evolutionary prerequisites. Its edge-of-void location also informs cosmological structure formation studies. The local void is a vast, underdense region whose shape and dynamics influence the flow of galaxies in the surrounding cosmic web. NGC 6503, being on the threshold of this void, acts as a tracer for the void's expansion and gravitational profile. Its peculiar velocity, how it deviates from the Hubble flow, provides clues about the forces acting on it, and by extension, about the distribution of dark energy and matter in its vicinity. It is not just a galaxy in isolation, it is a sensor embedded in the fabric of space-time, recording the very shape and motion of the universe. Importantly, NGC 6503 teaches us that galactic beauty and structure do not require drama. While galaxies like the antennae or the Milky Way owe their splendor to violent histories of collision and merger, NGC 6503 is a reminder that quiet persistence can also yield complexity and grace. It has built its stars, shaped its arms, and grown its halo not through theft or chaos, but through patience, spinning slowly in the cold, forging light from gas, and resisting the pull of every cosmic storm. In practical terms, its study benefits galaxy formation models, dark matter simulations, chemical evolution frameworks, and star formation laws. But in a more philosophical sense, it teaches humility. NGC 6503 is a whisper in a universe of explosions, a galaxy that chose a different path and still managed to thrive. It tells astronomers that sometimes, the best laboratory is the one left alone. In the grand theater of the cosmos, where galaxies clash like titans, where stars are born in brilliant bursts and die in supernova silence, there exists a small, luminous spiral on the edge of everything. NGC 6503. The galaxy that escaped the crowd. It doesn't blaze across the sky with the notoriety of Andromeda or whirl in majestic grandeur like the whirlpool. It doesn't sit at the center of a bustling cluster, or wear the battle scars of ancient collisions. It chose, or perhaps was chosen, to exist on the outskirts. Quiet. Alone. Unbothered. And in that quietude, there is something profoundly cinematic, something that resonates with a deep and timeless solitude. NGC 6503 orbits like a lone dancer at the edge of a cosmic ballroom, tracing its spiral steps in isolation, unseen by partners it will never meet. Its beauty is not born of chaos but of order, not of violence but of self-sufficiency. It spins not because it was set in motion by another, but because that is its nature. A celestial compass needle pointing inward to its core and outward to infinity, simultaneously. As we gaze upon it through telescopes and radio arrays, we are not just seeing a distant smear of light, we are glimpsing a chapter in the story of the universe that few galaxies can tell. The story of independence, of grace without interference, of formation without fury. NGC 6503 is what the universe looks like when it builds without breaking, when it shapes without struggle. It is the blueprint of what might have been for countless galaxies, had they not collided, consumed, and been consumed. The name, Lost Galaxy, suggests absence, forgottenness, a sense of disconnection. But perhaps it is not lost at all. Perhaps it is exactly where it's meant to be, far from the gravitational noise of its neighbors, carving its own fate in the margins of the void. It is not lost, it is free. Free from the rules written by density, mass, and mutual destruction. In the silence of the local void, NGC 6503 whispers a different kind of cosmic truth, that not all growth needs competition. Not all galaxies need company to be complete. And when we look at it, we're not just seeing what it is, we're imagining what it means. What does it say about us, that we find such poetry in something so alone? Do we see a mirror there, of our own longing for solitude in a world of noise? Or a lesson, that even in the emptiest parts of the universe, life, light, and structure can emerge and persist, and even thrive? As the stars of NGC 6503 continue to form and fade, as its spiral arms slowly unwind across the eons, its isolation becomes not a weakness, but a canvas. One upon which nature has painted a galaxy untouched, unhurried, and unbroken. A record of cosmic patience. A map of time traced in hydrogen and light. So, let us remember NGC 6503 not just as the galaxy on the edge of the void, but as the galaxy that reminds us, sometimes the most remarkable journeys happen far from the crowd. And in the quiet dark between the giants of the universe, one small spiral spins in peace, watching, waiting, and writing its own story in silence. This was the story of the galaxy that escaped the crowd. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.